Great, so welcome back to another video tutorial, and what we're going to go through today is inferential statistics and the important past paper questions on this topic that you should know. So just in case anyone doesn't know it, you should look up what the word inferential means and then look up what the word inference means, okay? Just do a Google search on that so you understand a little bit of what inferential statistics is doing. It's important to understand those words. But anyways, what you're really here for is to see some past paper questions solved. So there's about 68 pages in this document. And yeah, as always, I have a few red stars beside the most important ones. So we're going to get straight into it here. So as always, when I'm once I've them kind of set up the problems, pause the video and give them a go, because that's the way you get the most out of the videos. Right. So two independent samples of different sizes were taken from a population. The first sample size, N1, and the second sample size, N2, right? 95% confidence intervals for each sample. It was found that the margin of error. Now this is, you see, it's very complicated, dense language. This, and you need to somehow break it down. It's a bit tough. So we'll try and read this bit slowly. Um, it was found that the corresponding margin of error in the second sample was half that of the first sample. So we need to somehow convert this statement into something with algebra in it, right? So first of all, margin of error. So we'll call margin of error ME. Capital ME is a good symbol for that. And the less accurate formula for margin of error, which is kind of implied what we're doing in this question, is the 1 over the root n. The more accurate one is when you have like a p hat, but that's not what this question's implying. Okay, so this is our margin of error. So what we have is we have ME, you could say a 1, and then that's your margin of error for the first sample, N1. Hopefully that makes sense to people. And then we can have a margin of error for sample 2. And this will be 1 over root n2. So this is good now because ME1 and ME2 are what they're on about here in this underlined thing in red. So we need to set them equal to one another like this. Now one is bigger than the other one, okay? So at the minute this equal sign is a bit busted, it doesn't work. But we need to read the statement carefully and see who we have to kind of, if one of them is half the other, one of them needs to be multiplied by 2 to be made equal. So we need to work out which one is smaller. The corresponding margin of error in the second sample was half that of the first sample. Right. So I see that the second sample seems to have a smaller margin of error. So I'd multiply him by 2 to pump him up in size so he can be set equal to margin of error 1. So another way you could do that as well, you could kind of go with a half here, ME1, if that made sense to people, equals ME2. But I like this of setting them equal and then working out who's smaller and then kind of pumping them up that way. Okay, yeah, that seems right to me. So what we'll do now is we'll do the algebra. So we won't be able to work out n1 or n2. There's not enough information for that, but we'll be able to work out the ratio. So let's sub in here. 1 over root n1 equals 2 multiplied by 1 over root n2. Now it makes sense to square both sides. So when you square both sides here, you get 1 over n1. Now the 2 gets squared, it becomes a 4, and then this becomes it's kind of an over, that's a 1 over a full n2, if that makes sense. So then you can just multiply across, and you see n2 over n1 is 4. Okay. The hardest part of that question was breaking down that red statement there, okay? That red statement was a bit complicated to break down. So hopefully people learned from that. So I'll clear this away and get us set up for our next question. Okay, so this is our next question here. We have, it's kind of, I think, from the same mock paper, 2025. A survey was conducted in Cork on the popularity of a certain calculator known as Brand A. So the survey found this number of students out of this number of students use Brand A. So you can see there's probably a p hat going on there. Okay, so we'll snip this, make it bigger, this question. So we can see p hats involved here somehow. Construct a 95% confidence interval for Brand A. Give your answers to 3 decimal places. And then this assumption, this is a really big thing here at the end. So hopefully I remember to do this for you. So obviously pause the video, give this a go. So this is our formula for when we're constructing a 95% confidence interval for a portion. We should all know this formula off by heart. So it's p hat plus and minus 1.96 square root. Now the formula is normally meant to be this, okay? So this will actually tie in with our assumption. I can actually discuss the assumption now. That's the proper formula there, right? But we don't know p. We don't know, p hat is the sample proportion and p is the population proportion. And we don't know the population proportion. So our best estimate of P is P hat. And that is the assumption. It's because we don't know, if you wanted to put this in words, it's that P hat is approximately equal to P. Okay, in other words, the way to write this is our sample proportion, and you make a flashcard on this, sample proportion is what's known as a good estimator of P, which is the population proportion, okay? And you can also add a line to that there, because we do this because we don't know P, the whole thing. We'd have to do like a big census. You should know the difference between a census is when you ask like the whole country, for example. And we need to do a census on this, and that's too expensive or whatever. So our sample proportion is a good estimator of the population proportion. So that's the assumption. And as you can see here, the formula requires P, but if we don't know P, we use P hat. Okay, so that makes sense to people. So you can just sub it in like this, the examiner like this, 1450, rather than using a calculator. You can just use a calculator once, unless they explicitly get you in a part, say, a part before this to work out p hat on its own, you know. Sometimes they do that. 86 over 150 over, so there's nothing wrong with this. This is actually the preferred way to write something like this out. Showing you subbing in, you know. All over 1450. Now, once you do that, you write down in the middle here P. Okay, because we're trying to bound P here in this confidence interval. So you have P is going to be less greater than something here, and it'll be less than something. So what we do is we set this up in our calculator, and then when we use the plus, it'll be this value here, and then when we use the minus, it'll be that value there. So I'm going to pause the video, type that in here because I don't want to waste time. Okay, so I've typed that in here. So when I have it with the minus, I get this number here, 0.65, and it said 3 decimal places. Now it didn't say as a percentage, so you got to be careful here. So sometimes they'll want it as a percentage, but that's not implied here. So we'll give this as a decimal, 56. So then it's really easy. You just go over in your calculator, delete the minus, put in a plus, and you get 0.704. Now, if it wanted that as a decimal, as a percentage, we'd call that 65.6% is less than P is less than, what is it, 70.4%, okay? But that would only be one decimal place on the percentage, so you got to read the question carefully for what they're on about. Grand. So that's what this means is we're 95% confident that the population proportion is between these two values, okay? Great, so that's because sometimes they ask what does it mean, you know? So hopefully people got that. I think the next part here is being used as well. So I'll keep this here. So this is our next question. Determine the sample size that will have the margin of error for this for the population, for the proportion, okay? So that's kind of a bit tied into what we seen there earlier on in the first question of this video. So let's have a look at the formula and what actually is the margin of error. So as we seen there a second ago, this was the formula, the 1.96 square root p hat when we don't know p over n. Right, so we're looking to change the sample size so that the margin of error, what I am circling here, this is the margin of error. That's the more accurate ME formula, okay? It's more accurate than the 1 over root n formula that you've seen earlier on. So we want to half this guy's size, right? And we're going to change n's value. So very simply, right, if you want to, all of this will remain constant except for the n. The n is the only thing that can change value. And it's great if you can see that if you put a 2 in here, it won't half me. The reason it won't half me is because realistically, when you're square rooting a 2, it's like you're dividing by a root 2. Yeah, fair enough, the root n is down here, but the point is that you haven't actually halved the margin of error if you just put a 2 there, because you've only really reduced its value by root 2. So hopefully people are good with this idea. If you put a 4 here, right? If you put a 4 there, what actually happens is the original margin of error has gone down by root 4. And that's the same as having halved it, okay, when you divide it by 2. So the answer to this here is the sample size has to go up. If it was originally n, it has to be 4n. And so the sample size up here was this. So the sample size needed down here is 4 times 40. Okay. Um, so hopefully people, so the answer there is 5800. Now, hopefully people understand that. If you didn't understand that, what you could obviously do is, right, you have the p-ats from before. So what you can do is you can just work out what the ME part was from before. I could probably get it here if I haven't. Oh, it's gone now. But you can just work out what the p-hat was from, what the ME was from before, and then just double your n, and you see you haven't half the ME, and then bring it up by 4, and then you'll notice you have um, halved whatever ME worked out to be. Hopefully that makes sense to people. Let me see, is there anything else I can do to help there? I could probably work out the value of ME from before, so let me pause here and do it. Okay, so I brought up what we had before. This is the way we worked out the confidence interval from before, and as I said, this was the margin of error, the thing we add and subtract. When you type that into your calculator, the original margin of error works out as about 0.024, and we'll use a bit of accuracy here, which says 0.01, okay? Now, they said they wanted the margin of error to half, so then you just say that the new margin of error, you can call it ME new, is equal to half of this, so you just divide it by 2, and you'll get 0.0. So this is another way of doing this question if you didn't just see how obvious the 4 thing was. 12005, right? So then you just work out what n is as an unknown. So what we'll do here is this. So then this is, we set this equal to what this is here. So then you go 0.012005 equals the 1.96 square root, the p hat, which is 986 over, so I kind of ran out of room, but you get the point, 986 over 1450, that's a 14, and then over an unknown n, okay? So let me move that down so people can see it, because some people won't have realized that you can just divide by the n just has to get 4 times bigger. So you see this here, look at this, what I worked out in green. So I just halved the original margin of error, and then I put in my original p hat, which hasn't changed, and then now I have an unknown n. And I want you to go and do the algebra on this, so where you kind of square both sides, and then move it around, get n. And if you do that, you'll see that n works out as, what was it, 5800, I think, from before. And that is just 4 times our original n's value. So you can see, but it's much better if you can just realize that all you have to do is multiply by 4, because, you know, this is being square rooted, so the square root of 4 is the same as like halving the original margin of error here. Okay, I hopefully explained that fairly well to people there. Okay, so I'm going to pause here, scroll on to the next question. Oh yes, there's actually another interesting part to this one here. So where they're like, there's another 3 surveys about this brand calculator A, and they've got a survey 2, survey 3, survey 4. So each of them have their own p hat, okay? So what we need to remember from before, remember we had our confidence interval. So it was like p less than, oh, let me try and remember what the values were. I can probably do it here. 986 over, oh, let me, 986 over 1450. Yep, so it was between 0.704 and then it was greater than 0.656, as you remember. Now all you do here, this is pretty straightforward, is you just work out a p hat for each of these surveys, and whichever one is not in our interval here, it's the one that's most likely to have not occurred in Cork, if that makes sense to people. So like when I work out the p hat there for survey 2, 30 over 3500, that's working out as 0.51, so that one's outside the interval, so survey 2 doesn't look like it was conducted in Cork. The other one, 1073 over 1620, so that works out as 0.66, so that's in the interval, so that's good. And then the other one is 2388 divided by 3500. And again, that's in our interval again, that's 0.6823. So the justification for this is that this p hat for wherever this survey 2 was taken is very different to what we estimate the population proportion to be for County Cork, where this was from. So maybe you go outside Cork and the proportion changes value, you know. And that's kind of what that looks like there. Okay, so hopefully that makes sense to people. And the justification is just this value was outside our interval before. Okay, so little small question for a few marks. All right, I'll pause this, get us our next question. Okay, so moving along here, we've a 2024 paper 2, question 7, and it's a hypothesis test. So you see we have a conclusion, a reason for your conclusion, and we state the null hypothesis and such. So obviously give this a go yourselves. See, can you get it out? And I'll do it here as well. So in 2020, as it says there, PK were rated the best hotel chain by 75% of customers. So that nearly tells us what our H0 is going to be without reading any further. H0 loves the original claim to be true. It wants there to. H0 is this no change, no difference statement. So straight away I can tell you that H0 is going to be saying, oh, this looks like a proportion as well. Yeah, this is proportion. So it's going to want to say that the proportion, not an equal sign here. So we do 2 dots, as in this is what H0 says. It says that P is still 0.75, So then that nearly tells us then what H1 is without reading any further. This one is going to be the alternative hypothesis. H1 is always like, that guy loves change. He wants there to be a difference. In other words, he wouldn't want the original claim to be true anymore. He'd want it to have changed. So we'd say that P does not equal 0.75. And then spell this out then for the examiner. Not only state these, but then also say that, repeat this statement here. PK hotels were rated, they're rated best hotel by 75% of customers. That is what H0 is saying. And then a shorthand way of saying that is P equals 0.75. And then this guy's worded statement is PK hotels are not rated the best hotel chain by 75% of their customers. Okay. Anyways, so let's do the hypothesis test at the 5% level of significance. So we get a p hat in this question. The p hat is 756 over 1,000. Okay. And then the way we do these hypothesis tests is we construct the confidence interval and see if the 75% is within it. Okay. So let's do this. So we go p hat. We'll use this format, p hat plus or minus 1.96 square root p hat 1 minus p hat over n. N will be 1,000. This will be our p hat. And then we'll get a confidence interval with our p in the middle like this. Okay, so I'm going to pause the video, do this because I've already kind of subbed something like this in before. Okay, so I typed all that in there into my calculator, like what we done in a previous question. So this is what the confidence interval works out to be. If they don't tell you like what numbers of decimal places to always use, 4 is always good because then that makes the percentage look quite nice like this. We have like 73, basically 73.87% is greater than P, and then that's less than 79.13%. So what that means is we're 95% confident, right, that the population proportion of people who look at this hotel chain, they think it's the best between those percentages. And as their claim here of 75% is within our interval, that means the claim is good, okay? So that means H0 wins here, okay? So if the P is within this interval, their claim, that's good for H0. So basically what we do here is, as you've seen there, there's a conclusion down here. So our conclusion is that P does equal 0.75, right? And then the conclusion is that, yes, oh yeah, you have to state this as well. We do not reject H0, and we reject. So you always say, you don't say accept, you say you do not reject one of them, and you say who you reject, and that's it. And then that kind of means, therefore, you'd restate this. PK hotels are still rated the best whole chain in Europe by 75% of their customers. That's what you'd write out. I'm not going to spell it on the Zoom here. And then you were asked for the reason for this. So the reason is as their claimed P equals 0.75 was within our 95% confidence interval. Okay, confidence interval. So it's a bit annoying having to spell this out in the Zoom, but you get what I'm saying in verbal words. Okay, so if their claimed P is within our interval, it means that the 5% level of significance, their claim is good. Okay, so H0 wins, it doesn't get rejected, and H1 gets rejected. Okay, that's a pretty bread and butter question, and knowing this formula off by heart for this and how it goes down is how you get full marks pretty easily in a question like that. Okay. So yeah, I think that's the end of that one. So yeah, straight on here is the next question. I don't need to pause the video because it's straight afterwards. So this is something to do with the Rugby World Cup here, so we'll do this question. So it is widely believed that the average number of tries scored per game, per match, is 5.9, with the standard deviation of this, okay? To investigate if this claim holds, they done a sample, right? They went and got a sample, so then they got themselves a sample mean, obviously. Where is it here? Their sample mean is 6.4. Constructed a 95% confidence interval. So again, this is a formula we're meant to know off by heart. A 95% confidence interval, when we're doing sample means, we use x bar plus and minus 1.96 square root sigma over the square root of n. Okay, so you gotta know that formula off by heart there, right? So let's sub into that because you see we have everything. We have our x bar. So we use the sigma they give us then there, and then we have our n is 36. So let me sub it in here for the examiner. 6.4 plus and minus 1.96 multiplied by, what is it there? It's 1.8 over the square root of 36, which will become 6 when we're doing the calculation. And so then what we put in the middle here, like you know how we put p the last time in the middle, we put mu in the middle here, okay? So let me go and work this out here, and then I'll resume. Okay, so when you use the plus version of this, you'll get yourself 6.988. Did it say 3 decimals? 3 decimals. It doesn't say how many decimals places, but 3 looks good when you type it in terms of not rounding it too much, you know. So then this is 5812. Right, so there's your 95% confidence interval. So then the next one here is a hypothesis test, right? Conduct a hypothesis test at the 5% significance level to determine if there is enough evidence to suggest that the mean number of tries has changed. So you can nearly know what the conclusion is already here. Because the 5.9 is within the interval, H0 is going to win. But we'll go ahead and we'll do this anyways. So let's see how can I make room for this. I could probably do it here. It'll just be a bit messy. So we need to state H0. Remember, H0 is the no change. He'll want there to be no change. So he'll want mu to still be equal to 5.9. And then you want a worded statement for that, which is that the average number of tries scored per match is still 5.9. Whereas H1 will be like, no, there's been change. It's no longer 5.9. It's not equal to 5.9. And you would say the average number of tries scored per game is not 5.9 in words for the examiner, okay? I'm not going to spell it out in the Zoom here. So what we'd usually then do is work out a Z-score for this, but you could also use your confidence interval, like I said there. Using your confidence interval, the 5.9 is in here, so that's good, the H0 wins. But we'll do the Z-score version as well. So Z equals X bar, good to know this formula off by heart as well, minus mu over sigma over the square root of n, right? And then the Z here works out as, our X bar was 6.4 minus 5.9 over 1.2 over the square root of 36. Okay, and then you work that out, and we'll compare it to our critical Z-score, which I'll talk about in a sec. 1.2 over 6. So there we go. What are we getting there? Ooh, 2.5. Did I type something in wrong somewhere? Let me see. Oh yeah, I did. Yeah, so it's not 1.2. Because the reason I knew something was wrong there is because that is above 1.96, so then we'd be rejecting H0 there. But you can see there I meant to type 1.8 there. And so this is better now because this is 1.67. And what we know here is our critical Z-scores. We should know our critical Z-scores. If we draw this diagram here, we should all know this diagram. It should be in our flashcards. So you have the 0 in the middle there. And then these are the critical Z-scores of minus 1.96 and plus 1.96. And so outside of these, if you get a Z-score outside of these, the shaded region I'm shading in here, that region is called the rejection region, okay? And who gets rejected in there? If you get a Z-score in there, H0 gets rejected. Now look at this. We are not in the rejection region with 1.67. We're kind of like in here. So we're H0 is safe in there. And so you just make that conclusion then for the examiner. As this is less than 1.96, therefore do not reject H0. Do not reject H0. And then you make the statement here, I'm not going to spell out, you would write reject H1. And then you make a conclusion. Your conclusion will be this. At the 5% level of significance, okay, we can conclude that the average number of tries per match is still 5.9. Okay. Basically, you just restate what we wrote out here in words here after you define your null hypothesis. Okay, so hopefully people are good with that, and this diagram here on the rejection region, very important. Okay, cool. So we'll crack along there. Yes, so there's a p-value for this thing here. So we have to talk about p-values, right? So we'll do a quick thing on p-values, and we'll try and bring up our calculations there from before without it getting too messy. So we got a z-score there, remember, of 1.67, right? We got a z-score of 1.67. So now we're asked to calculate a p-value and then interpret it, right? So we're going to talk about what p-values are, but first of all, we're going to calculate it, right? So the formula for p-value, people should know this. Loads of people, of course, though, are scared of p-values. They don't know what they are, right? So the first thing you've got to understand about a p-value, it's just an area, okay? That's the first thing I'm going to mention. So all we're doing is we're working out an area underneath the curve. And the formula for doing this is 2 times 1 minus the probability that z is less than the modulus of the z, we'll call it z1. That's our test score. That's this, I'll call that z1 if you want, the 1.67. So what we do here, and that's a good formula to know off by heart, you kind of have to know it off by heart. So our p-value, what this is getting for us is it's getting an area underneath that curve. So we'll work it out here first of all, and then we'll talk about it with a diagram. 1 minus the probability that z is less than 1.67. Now, to get the probability that z is less than 1.67, if that was minus 1.67, we'd still be getting what's less than plus 1.67 because of the way the formula works with the modulus. So yeah, so let's do that. Let's go to our formula tables and see what's below 1.67. Okay, so we're in the formula tables here, and we can see what's below 1.67. This formula tables always gives you what's below the z-score. So what's below 1.67 is this number here, 9525, easy number, remember, okay? So let's go here. What did I have? I have this here. So I don't want the question to completely disappear on us. So yeah, we'll keep going with this here. This looks good. So the p-value itself here, when we sub in, it will be equal to p-value equals 2 times 1 minus the thing we just read from the tables, which was, what was it, 9525? 9525. So hopefully this isn't too messy for people and they can track it. So what we're going to get here is an area when I type this into my calculator. So this is going to be 2 times 1 minus 0.9525. So I'm after getting myself an area of 0.095, all right? 0.095, it's just the way that worked out. Okay, so what is that? We need to interpret what this thing actually is, okay? And how it compares to our 5% level of significance. So we're going to go off on a little detour now so we can explain what p-values are for people, okay? Okay, so I've put it in here with a little bit of a supplement to the explanation I'm going to give you. So this supplement will only last maybe a minute or two, and then you'll be back with the normal video. So I've done this little bit of an infographic to kind of help people understand p-values. So what we have basically is what I've kind of already mentioned to you, that this is the formula for your working out your p-value. And as you can see, the owl telling you here, p-value is just an area, okay? And alpha is our level of significance. It's like the size of the rejection region, okay? And alpha itself is its own area, as we know it's a 5%, 0.05. So for all our sort of leave insert questions, alpha is always set at 5%, you know? That's from our 95% confidence intervals kind of thing. So as we scroll down here, I have a few scenarios here so you can understand what I've been saying about what the p-value is. So the technical definition, as we said, about a p-value is it's the lowest level of significance at which H0 begins to be rejected. And so we're gonna try and make sense of some of that here in the diagram. So I'll build some of them up here. So let me cover up these ones for a second. Okay, so what do we have here? So we have, this is our typical rejection region. See our 1.96s and then see the 0.05. Okay, so that's the size of our rejection region. And then we're taking an example here if we have a p-value of 0 0.3. So look at what happens. Look if we dash down the rejection region here. Look at where our p-value is. Our p-value is the blue area. It's in the rejection region. And so if you're in the rejection region, your p-value is in the rejection region, you reject H0, okay? It's a little bit more complicated to think, oh yeah, that the p-value, if it's less than the level of significance, you reject H0. I think it's better and more visible to just think about, where is my p-value? Is my p-value inside the rejection region? And if it is, well then you reject H0, okay? So then let's do another one. So there's another type of test that we do. So we do, well, we don't do it on the Leaving Cert, but they do it in real life. So they do 99% confidence intervals, okay? And so they will be done at the 1% level of significance, okay? So we can see an example here where alpha is 1%. Now, this infographic isn't drawn very to scale. As you can see, this is minus 2.58, and this is a much smaller area than this, but they drew the area here to scale. So realistically, this shouldn't be here. Hopefully that makes sense to people, because this is, uh, if alpha is only 1%, that red area, this rejection region, should be very, very small. Okay. Because it's like, as you can see there, it's only 0.005 in area, whereas this was 0.025, so it's much bigger. Okay, so all that's left there is the little red tails on the end. And as you can see then, when I dash down those red tails, look at our p-value. Our p-value in blue is not in the rejection region. See, it's escaped out. Okay, a little bit of it's in there, but most of it is escaped out of the rejection region. See it here in blue. And so we do not reject H0 in this scenario. So absolutely, when the p-value is 0.03 for our normal tests, say alpha was 5%, H0 gets rejected because the p-value is in the rejection region. But if the level of significance was 1%, you would not be rejecting H0 because your p-value escaped the rejection region, as you can see here. So that brings us, and people should understand then that the level of significance and the p-value are related to one another in the sense that you get what I'm saying. The p-value is the lowest level of significance at which you start to reject H0. So as you can see, H0 wasn't rejected here. H0 was rejected here. So then what is the lowest level at when you begin to reject H0? It's when the alpha is the p-value, and that's what this is here. If you make up your alpha to be the exact same value as your p-value, as in the level of significance and the p-value are exactly the same, well then the size of the rejection region and the size of your p-value are identical. And so because they're identical, the p-value hasn't fully escaped the rejection region, so it just gets rejected. H0 just gets rejected here. And so the idea is, hopefully people can understand from this, is that that's why we say the p-value is the smallest level of significance at which H0 begins to be rejected, okay? And so hopefully that makes sense. P-value is just an area, and then when you're understanding its technical definition, that's what it means down there. So if alpha is 5%, your p-value is 3%, H0 does not get rejected. If alpha was 1% though, your p-value is 3, H0 does not get rejected. And then this here, when alpha is this, the lowest level of significance at which H0 does get rejected. So hopefully that makes sense to people. So I'll let you back to the video. So now that we have a good p-value in this question, so let's get ourselves a bit of area here. Right, I said to you, if you didn't know what a p-value was, a p-value is an area. Okay, so as this is our usual bell curve with a 0 in the middle. So what the p-value is, remember we got a z-score in this question. Okay, we got a z-score here and it was something like 1.67. Do you remember we got that? So what the p-value is, it deals with its mirror as well down here, minus 1.67. The p-value is this area here. The p-value is the area outside of your test score that you work out in the question. So those two pink areas added together, when you add them up, that is the p-value. So that formula I gave you there a second ago, that the p-value was equal to 2 times 1 minus the probability that z is less than the modulus of the test score that we were getting there a second ago, where that is the 1.67. That formula there gets you, the reason there's a 2 there is because it's doubling, it's getting 2 times this area, okay? So you should all know how to get set areas under the curve. The reason there's a 1 minus there is because it's going and checking what's below it here, and then going 1 minus it because the area under the whole curve is 1. So that's why that formula works. Anyways, that's not the main thing here. So what you've got to understand anyways is a p-value is an area under a curve, right? And it has another very technical definition that you need to understand, right? The p-value, right? It's this thing here, and you'll learn this off by heart, and I'm going to write it out as neat as I can. It's the lowest level of significance, and this will cover you for your questions. The lowest level of significance at which H0 begins to be rejected. Right, so we're going to understand what that means, okay? So before, in this actual question that we're doing right now, the level of significance was set at what? So we should remember that the level of significance was at 5%. Do you remember that? And where does that 5% come from? So you might know we have our, remember our rejection region. Let me put it here. Remember it's 1.96 and minus 1.96. So if you work out the area below 1.96, minus 1.96 and above 1.96, that works out as 0. Each side has 2.5%. So when they add together, that's where the 5% comes from, okay? When you add this with this, okay? So that's where the 5% level of significance comes from. And so then if your z-score is in this rejection region, you reject H0. So the idea is if your p-value, say, remember the p-value is an area, if your area is less than 0.05, it means that you're in the rejection region down here. It means it's not good and H0 loses out, okay? But look at this p-value here that we got in this question. Remember, what was it? The p-value in this one here was 0.095. Notice it's a 0.95. Okay, it's nearly like 0.1. That was bigger than the rejection region down there, so H0 didn't get rejected. So how does this tie in with the question? Why is the p-value also known as the lowest level of significance at which H0 begins to be rejected? Right, so what you've got to understand is this. We do in Leaving Cert Maths these 5% level of significance tests all the time. It's always 5% level of significance, and we always then do 95% confidence intervals, right? So there's actually other types as well. So you can do things that are like 99% confidence intervals. And so then you're at the 1% alpha is what we call the level of significance. Alpha would be 1% level of significance, right? And then there's another one, significance. There's another one. There's a 90% confidence interval. And so then alpha equals 10%, right? That's the level of significance. Now, why are we bringing that up? So think about this now, okay? At the 5% level of significance, this p-value survived. In other words, H0 got to live when this was, it only had to beat the 5% level of significance. But if alpha was 10% and the p-value was 0.95, well, then we're going to start rejecting H0. That, when basically this p-value, if the rejection region is set when alpha is 10%, this then is smaller than it. So what happens in this scenario, you would actually reject H0 if alpha was 10%, but you do not reject it when it's the 5% it was in this question. So hopefully that makes sense to people. Hopefully I've done an okay job at explaining that there. So this really matters down here, that the p-value is the lowest level of significance at which H0 begins to be rejected. And so when the level of significance was 5% and our p-value was this, it didn't get rejected. H0 didn't get rejected. But if we were doing another type of test where alpha was 10%, then it would have gotten rejected, okay? So hopefully that makes sense to people. Great, so we'll pop back to the book. And so yeah, they make us down here interpret what it means in the question. So we got something like a p-value equals 0.095. And interpret what it means is at the 5% level of significance, you know. And yeah, you'd state as well here that it's the lowest level of significance at which H0 would be rejected. In other words, the number of tries wouldn't be the 5.9 it was before. So at the 5% level of significance, the number of tries, the mean number of tries is 5.9. But then you can also do an alternative, but at the 10% level of significance, say. The 10% level of significance. The mean number of tries, we'd have to disagree, is not, you'd write is not 5.9, okay? So hopefully I'm not waffling on too much there, but people get the point on what you're kind of meant to write in there, okay? So yeah, that's the lowest level of significance at which H0 begins to reject it, and then we write out an example of it here. At 5%, we don't reject H0. In other words, the mean number of tries is still 5.9. And then, but if you were at 10%, well then it's the mean number of tries is not 5.9 because H0 gets rejected then. So hopefully that makes sense to people on what the p-value is. Okay, so we have another question here. The weight of stones in a bag at a garden centre are normally distributed, and they have this mean and standard deviation. And then we're given a random sample of 50, so that's probably our n there. So obviously pause the video, give this a go, and then we'll do this thing with the limits down here, and then there's a part C to it. Okay. So find the probability that the mean weight is less than this. So what we want, we're talking about the mean weight here of the sample. We're testing a mean weight of a sample. So we can convert that statement there. It's the probability that X bar is less than 49 GM, right? So we then need to convert that into a z-score so that we can go and use our tables. So to use the tables here, we need a z-score. So because we have a sample mean here, and what they're talking about is comparing how a sample's mean weight to this. So we use the formula that has the n on the bottom. So it's x bar minus mu over sigma over root n. So there'll be a good complicated example later on in the videos on inferential statistics where they actually do give us an n, but we're not actually meant to use this formula. So that's a really tough, interesting example. So let's work this out here. This will be 49. This is our test x bar. That's what we're typing in there. 49 minus 48.6. That's the mu they give us from the question over a standard deviation they give us in the question over the square root of 50. So we get ourselves a z-score for that. Just want to take a second to type in 49 minus 48.6. 8.5 over root 50. So we're getting a z-score there of 0. Usually 2 decimal places is what you want because your tables book only works to 2 decimal places for this. So then what you do is you convert that statement there, probability that x bar is less than 49, to this statement. It's the probability that z is less than 0.33. And the great thing about that one is you can just read that one off the tables book. You just go 0.33 and the answer to this is 6293. So the probability of this is 0.6293, and if you gave that as a percentage up here, it will be like 62.93%, okay? So hopefully that makes sense to people, particularly you want to get into this good habit of being able to write a kind of x bar statement and then write the equivalent z bar, or the z score statement, okay? Right, I'll clear this away and get set up for part B. Okay, then the part B here is find the limits within which the central 95% of such sample means lie. Now that is an extremely complicated statement there, and hopefully you've given this a go and try and work out what they mean there. That is an extremely complicated way of saying construct a 95% confidence interval for how the sample mean should be distributed around the mean. Okay, that's literally just construct a 95% confidence interval, and the limits are obviously the end of the interval. You know, when you have mu is less than this and there's a number here and there's a number here, they're the limits. Okay, so that's what this is. So very complicated language. So that's kind of why I picked this one here, because of that. So again, we'll have our x bar plus and minus 1.96 sigma over root n, and for this here we have two means here. So this is a good question. So you have a question here for yourself. Do you use the X bar that they have given us here, or do you use the original one in the question? So have a think about that here and see what you think. Yeah, so hopefully people had to think about that. So the idea is here you want to use the actual known mu, okay? If you know the mu to go and use it. Whereas here, this was just kind of an intended thing for the first part of the question. This wasn't like this is your X bar that you recorded from going out and carried out a sample. Because usually what you don't know the mu, you know. So that's when you construct these, you're trying to work out how based on your X bar, how much above and below. You're trying to get an estimate of where mu is, but in this scenario here, we actually know mu. So what we're going to type here in for X bar will actually be the mu, okay? So hopefully that makes sense to people. So it's a good question in that sense. 1.96, 0.96 sigma over root n. I'll type in my sigma as well, my root n. And I was thinking of a good comment there that's going to explain why we use the mu there over the root 50. So then mu should be between, it should be between 48.6 plus 1.96 multiplied by 8.5 over root 50. So that comes out to be 50.96. And this has units as well. You can put this little GM thing, whatever the units means. So maybe it means grams or whatever. It should be just a G if it means grams. So then this is 46.24, right? So just on why we used a mu here, you might remember from this other formula where we have the p hat plus and minus. When we're constructing this 95% confidence interval, what we do, we go plus and minus 1.96 square root. And the formula is meant to be p here, right? But because a lot of the time we don't know p, what we do is we use p hat. And that's because p hat is a good estimator of what p is, the population proportion. And so the same thing here, a lot of the time we don't know mu, so we use x bar. And x bar is a good estimator of mu, but if you do know mu, like in this question here, it's good to use it. Okay, great. So we'll clear that away. So how large a sample will be needed in order that the central 95% sample means, again, the complicated language, would lie in an interval of width 4, 4, 4, okay? So what they mean is they basically want, if this here is the mean, they basically are talking about, well, what if this is like 50.6 and then this here is 46.6. So can you see what I done there? I went plus and minus 2 above what the mean is. In other words, we wanted what's called the plus and minus part here, this 1.96 sigma over root n. What we want to set this thing equal to is 2, because then you're going plus and minus 2, and that gives the interval a width of 4, okay? The distance between them is 4. So hopefully that makes sense to people. So what they've basically given us is an instruction here to set the thing we go plus and minusing. They sometimes call that the radius of the interval equal to 2. So we got ourselves an 8.5 over root n. We don't know n now because we're looking for a new sample. So then really just algebra here. So you'd bring the root n up and then you leave this here. No need to type it into a calculator. All over 2. And then you just square everything. So n would be equal to, so it's good to only have to use the calculator once, you know, over 2. And the examiner will prefer you moving it around like that as well, you know. So 1.96 times 8.5 over 2 all to be squared. So that there is working out as 69.39. So it's a little bit of a pain that now, because you're thinking, oh, do I round up or down? And they're not very specific in the question here. Oh, they are actually. They say at most, it's at most 4 grams. So we can actually test this properly. So you have two options here, whether or not you round up or round down. And it's never just a case of, oh, this is closer to 69, so we round down. You need to test both of them, okay? And the way you test them is by subbing them back in here and seeing which one does satisfies the thing they're on about here with the at most 4 grams as a width. So let's do that here. If we put 69 into this interval up here, what we're really going is plus and minus. So let's type it in. 1.96 multiplied by 8.5 over the square root of 69. So when you do 69, I'll write it above here, you're going plus and minus 2.0056. So you can see now that interval will be a little bit above 4. Okay, that won't satisfy this at most 4 thing. But if you change the 69 to a 70, you'll see that the thing you're going plus and minus is 1.99125. So then the interval isn't, it's actually a little bit skinnier than 4, and that satisfies the at most. And so the examiner would expect you to do a little bit of a check there. And then because this then would be wider than 4, and this thing is at most, fitting the at most, the correct answer is 70. And so you can see there, it'd be wrong to have actually rounded down, if you had to round up, and you had to check it. Okay, that was a good question there. Okay, so I think, what's the video on now? 46 minutes. So that's maybe a good place to stop here. And then in the next video, we'll pick up from this. In the next part of this video, we'll pick up from this one here with Fia owns a forest. Okay, so I'll stop it here. Hopefully you learned a few bits in this part. Great, so we're back for part 2 on important past paper questions you should know on the topic of inferential statistics. So we said we pick up here with this Fia owns a forest. Okay, so the heights of trees in a forest of this type are usually normally distributed with a certain mean here of 360 and a standard deviation of 27. Use this information to answer all these following parts. Okay, one tree is picked at random. Okay, so we're checking one tree now. So this isn't a sample. We're just seeing how one tree is distributed among this sort of population. So this isn't going to be where we divide by the n when we're getting a z-score. Okay. So find the probability that the height of the tree is between this and this. Okay. So what we do is, as I said, this isn't x bars, so this is x. We convert this into an x statement first. 390 and 330. Okay. So what we're going to do now is turn those x values into z's, z-scores. So the formula for this is x minus mu over sigma, no root n. And so we get 2 z-scores for this. We'll sub in here. So 330, subbing in the lower one, minus the mu, which is 360, over sigma, which is 27. And then the other one is 390, minus 360 over 27. Okay, so then you can basically, once you type those into your calculator, you can convert that blue statement there into this blue statement, which is with z's. Okay, so let's type that in. So 330 minus 360 over 27. So that's a z-score of minus 1.11, 2 decimal places always, because that's what the tables book works with. And then 390. So that then is a plus 1.11. Now that's an easy one because that's pretty symmetrical. But anyways, whenever we're getting this, what we always want to do, let me clear this away because we've gotten the z-scores, and I'll snip this so I can draw a diagram. So always when you're getting an area like this from the bell curve, you want to sketch it. Okay, so I said this is easy because the z value above and below is the same, and you got to get good at drawing these curves. So this would be part of your workings. So you do this for the examiner and for yourself. Okay, doesn't have to be 2 to scale. So there's our 2 z-scores. It'd be nicer if it was a bit more symmetrical, but it gets the point. So then you shade in the area that you're looking for. You're looking for this area. All right. So how do we get that area? Then you then kind of come up with a plan. So what you could do is, because our tables book will only tell us like what's below 1.11, so have a think about the quickest way to kind of get this this area. So I'm gonna pause this now and get my tables book ready. Yeah, so yeah, I forgot that's open from the previous video, so I don't need to get that open. Okay, so the way to describe how to get this region here is you take away 2 areas. Okay, so what you're going to do is you're going to get the area underneath all of this here that I've highlighted in purple, and then you're going to get the area underneath this guy here, and take them away, because if you take the purple away from the orange, you get the green, okay? So we write that in here, and you've got to show the workings for this for the examiner, right? So let me get a place to write this. I'll use red here because it's distinct down here. So this here, this area here equals the probability, as we said in purple there, that Z is less than 1.1. Take away the orange area, which is the probability that Z is less than minus 1.11. Now the great thing is we could just read this value from the tables book, but we can't read this value from the tables book. So the next line workings here is, we leave this one alone because we can just read this one from the tables book already. So we need to come up with some conversion for this. So the idea is that this orange area is equal to a symmetrical area above 1.11, okay, because everything's symmetrical. So hopefully that makes sense to people. So then we can swap this here for saying that that area is actually equal to what's when Z is greater than 1.11. Okay, so now we've gone from a negative Z-score to a positive one. Great. So we're closer now. So leaving this guy alone here, this is how your steps to workings would look. Now, we can't get what's above a Z-score from the tables. So what we do is the fact that the area under the total curve, I can do a separate diagram for this. Just people should know how to get Z-scores anyway, so but I'll do the tutorial here just in case people are rusty. So if you want to get this area that's above a Z-score here, the way to do it is to just get the area that's below it here in pink, say, and take it away from 1, because the area under the total curve is 1. So if you want the blue area, get the pink area and take it away from 1. And the pink area is what's below the Z-score you're working with. So the Z-score we're working with here is 1, 1. So we go 1, we go minus, and in here we swap this for 1 minus what's below it. So notice I go Z now less than 1.11. Okay, and the great thing is now both of them are, well, they're both the same, so this question was easy. But both of these can be read from the tables book, okay? So let's see what's below 1.11. 1.11, so 8665, okay? 8665, back here. So then you'd sub this in for the examiner. You'd go, I think 8665 I called out, minus bracket 1 minus 0.8665. And they'd be all the workings. You'd be expected to show all these workings and getting it. So this diagram was just for me showing you something. But this here was pretty important. So they're the steps. And then obviously pick up a calculator. 8655 minus bracket 1 minus 0.86655. So I'm getting that to be equal to, I ran out of room there, but that's equal to 0.733. Okay. So that's what's between those two Z-scores. Okay, so let me clear this away, get our next question going. Okay, so that's cleared away there. So the part 2 to this, obviously be pausing this, giving this a go. Every question I set up, always pause it, try to do it yourself. The shortest, smallest 5% of trees in the forest are not sent to the factory. Okay, as they are not tall enough. What is the minimum height that a tree needs to be in order to get sent to the factory? Okay, so what they've given us here is a percentage, and we have to work back to a Z-score. Okay, so what we got to do here is we got to do a bit of a diagram for ourselves. So you've got to get good at sketching these bell curves. Put the 0 in the middle. And now there is some unknown Z-score that we're looking for. And this unknown Z-score has a 5% area below it. Okay, so that area there is 5%. That'll be whatever they tell you in the question. If it was, 17% of trees don't get sent to the factory, this will be 17%. So we're looking for the Z-score that has 5% of the area below it. Right. So because this is going to be like a negative Z-score as well, just so we understand that, our tables book won't be able to help us with this at the minute. So what we've got to do is come up with a bit of a trick. So the idea is, if this is the negative Z-score, right, the positive Z-score, according to the symmetry, will have 5% above it. Again, our tables book won't tell us what's above a Z-score, but it will absolutely tell us the area below the Z-score here. So what we're going to do, we should know that this green area here, if 5% is above the pink Z-score here, 95% is below it. So what we're going to do is go to the tables book and find what Z-score has 95% area below it. Okay, and you do that here. Let me clear that away for a sec. Looking now, we're looking at the areas. So it looks like it's between here and here. See this here? So it looks like it's 1.6 It's pretty well split. So if you wanted an accurate answer, you could say 1.645, okay, to get the middle value. We will actually do that. We get a half decent answer here. So that's not what I wanted. This is it here. So then the z-score that does this, as we seen there, if your z-score is 1.645, you have 95% of the area below you. And so the actual z-score we're interested down here is minus 1.645, okay? That z-score has 5% below it. So that's our z-score. So the question isn't done yet. So we got to remember, we want to work back to a height. A height is an x. So z equals x minus mu over sigma. We've just got the z-score, and the trick here, people would slip up if they didn't include the minus sign. The x, which we're looking for, minus the mu, which was in the question, and over the sigma, which was in the question. So then you move that around, multiply this by 27, and then add 360 when you bring the 360 over. Plus, or take away 27 times 1.645. So I'm getting the height of the tree is 315.59. And then what did it say? Did it say round it in a certain way? Yeah, like it doesn't say to give it to any particular decimal places. The shortest three. So basically, as you can see here, the mean is about 360. So if the height of the tree is below this, it won't get sent to the factory. So this is like the cutoff point there. So if we were to kind of maybe round it up, we'd say if you're below 316, you don't get in, you don't get into the factory. Okay, hopefully that makes sense to people. So I'll pause that, clear it away. Okay, so we're back. So we just scrolled on to a next part here. So that was our previous one here. So part B here is a hypothesis test. And as you can see here, we're talking about a sample of 100 trees. So now we're doing the kind of the sampling an X bar. So the mean height of the sample. So you see that's our X bar now. Okay. Right. So this is a hypothesis test. Obviously, pause it, give it a go. I have a note up here to show you an infographic. So the reason why I'm going to walk you through a little bit of an infographic here for a minute is because when we do this question here, we're comparing the distribution of sample means. So our z-score formula is going to become this one. And like a lot of people are pretty uncomfortable with this. Like they know that they got to use this formula when the question mentions that there's a sample size of n, So they sort of default to using this. Whereas like in the very original one up there, we didn't use the root n because there was no mention of an n. You might remember this up here. Where we were comparing like a specific tree height of 390 and 380, okay? We weren't talking about them as if they were means of a sample kind of a thing, right? So we need to be able to kind of not just be relying on reading the question and being like, oh, there's an n in this question, so we need to use this z-score formula. So I have a little bit of an infographic for this, so let me get that up first before I do this question. Okay, so this is it here. There's a lot of information on this, but I'm going to walk you through it, and it'll hopefully help you think through the difference of this. So what we're talking about here is there's two different competitions as I make it out, individuals and gangs. And the gangs are going to be these sample means, right? So we got to tell the difference between which formula to use. So obviously pause the video and have a read of this first and see does it make sense to people. And then I'm going to walk you through it after you've had a read of it yourselves, okay? So the idea is we use this formula here when we're just comparing an individual value, okay? So you see each of these here, each of these businesses pay a racketeering fee to the gangs, right? So one individual fee is X, and each of these, see the bakery, the cafe, the auto shop, they all pay just this individual X. So we want to compare that to the mu, which is like what the whole city pays to them. So when you're comparing just one value, as he says here, is this one business that pays an 18% fee unusual compared to the rest of the city? So when you're comparing just one individual value like this, like Fia was with the trees there at 330, high 3 or 390, you use this formula, okay? But when do you use the formula that has the root n? So this is when you have, say, like a city like this, and within the city there are like, say, these small gangs. Now what the analogy here is these small gangs, these are like sample means, okay? So that's hopefully so people can make a bit of sense of this here. We're visualizing it in a kind of an example. Okay, so the idea is that look at what he's holding up now. He's not holding up someone's individual value. He's actually holding up an average that came from a gang, which is a group of members here, okay? So this 15%, it has to be compared to the sample size that you have here as well. So it's not, it's how does this sample mean compare to the mean of all the sample means. So this is what we call the distribution of sample means. So what I'm calling this here is x bar bar. Now we obviously know the formula, the correct formula for this has a mu here, but the idea is that this is part of the theory, is that the mean of sample means, in other words, see all these different sample means, their mean is equal to mu. Okay, that's the idea. The mean of sample mean. So that's why I go x bar bar. So x bar is a sample mean, and then when you go bar again, it's like the mean of sample means. Okay. So hopefully that makes sense to people. So we're comparing how this 15% average for this one gang compares to what the consensus is if we get the mean of all the gangs. Okay, we put all their averages together, like the 9.9 plus 9.6 plus 10.4, add them all together, and then divide it by 6, or how many gangs there are, in other words. So that's, as we say here, the X bar bar, the city consensus is that everyone should be paying 10%. Okay, and so then you see this random new gang that has a 15%. So they might look very unusual when compared to the 10% X bar bar, the mu for the city. So this is what I'm showing here, then an infographic here. So when the sample size is quite large, okay, when n is big, um, there's very little wiggle room that a variation has here, a 15%. But if the sample sizes are small, what happens is they don't have such a strong consensus, if that makes sense. So a new gang at 15% looks a little bit less unusual, whereas when they're all a large sample size like this 15% looks very unusual. And that's to do with, as you can see here, see this one is more spread out, and then this one's more tightly packed together. And that's because of the root n thing on the bottom, okay? So hopefully that makes sense to people. So it's a little bit of a complicated diagram, but it actually still explains a lot to people. So this is the big take home down here. So one person gets a sort of lot of wiggle room when you're comparing like one 18% value to everyone. But when you're comparing a whole like gangs percentage here, a whole sample means percentage, there's much less wiggle room, and that's why the root n is kind of on the bottom there. You're allowed a lot less wiggle room, a lot less variance, okay? Um, a lot less spread. Okay, so hopefully that makes sense to people there. It's a tricky thing to explain, which formula to use, and it's trying to get it packed in. When you're comparing just an individual value, you use this formula, and when you're comparing how one sample mean compares to what all the mean of the sample means are, that's the x bar bar, what we call mu. You use this formula. Okay. Great. So hopefully I didn't waste too much time on that, and we can get back to the question. So FIA claims that the mean height of trees is the usual height. So that means we're claiming that the mu is still 360. And so they've actually filled in the null hypothesis for us here. In other words, the shorthand way of saying this is that H0 would say, with the two dots here, mu is 360, and I think it has units, yeah, centimeters. And then the alternative hypothesis will be just to repeat this statement, and it'll be is not 360 centimeters. So say me writing it out there. And then you write, obviously that's called H1. And then you write the statement here, mu, the shorthand way, mu does not equal 360 centimeters, okay? So then they go off and they do a sample, and then here's one of their X bars, okay? And see, that's the kind of the size of the gang in the previous analogy I gave you there. So that's the n. So the n is 100. And then the X bar they got then was 350. So it's a little bit lower than the tested or the assumed claim here. Great. So let's work out a z score as we usually do for this. So z equals, using this formula, x bar minus mu over sigma over root n. So z then equals 350 minus 360 all over, they gave us a sigma in the question, did they? No, they don't seem to, but we'll be using the sigma from before. I'll scroll up, see what the sigma was from before. It was 27, okay? So we'll assume the same sigma here. So 27 over the square root of 100, which will work out as 10 when we're typing it in. So let's get a z-score for this. 350 minus 360, 27 over root 100. So you can see that's a pretty big z-score. That's minus 3.70. Okay, so that's going to be H0 is going to be rejected here because it's actually very far away from our rejection into our rejection region. It's very far into it. As we know, our critical z-scores are plus and minus the 1.96, and here what you would say for the examiner is minus 3.7 is less than minus 1.96, and then therefore what we do is we reject H0 because you're in the rejection region, you know. And so then we make a conclusion. So the conclusion would be this in words. At the 5% level of significance, we reject the null hypothesis, and we do not reject the alternative hypothesis, which means the mean height of trees is no longer 360 centimeters. Okay, so there you go. And yeah, so there was very little wiggle room there. So even though you're like, this is only 10 centimeters less, there's very little wiggle room because this is quite a large sample size, okay? So you're not allowed to have such a large variation here of 10 centimeters when you have such a large sample size. You can redo this question, say that the sample size was only maybe something like 30. When you redo this with 30, there's actually a question coming up on this later in the question. Now 30 still works. I want to go maybe something like, we'll do 20. Yeah, so if you had a sample size here of 20, you get a z-score of like minus 1.66, and then you wouldn't have rejected H0 in that scenario. So then that's the kind of thing that I showed you in the infographic. If the size of the gangs, the sample size is small, you get a bit more wiggle room, okay? But if you have a large sample size like this, having a deviation here of 10 centimeters, it's not allowed. It's too unusual. Okay, hopefully that makes sense to people. Okay, so there we go. So there's another 2 parts to this here, and I think that's, oh, there's even another part. There's a very long question here with Fia and the trees. So Fia wants to estimate the number of trees that have become infected with the disease. So there's some disease that was mentioned up here that was making the tree smaller. So we didn't read that out, but that's obviously stated there for anyone who paused it and gave it a go. Wants to estimate the number of trees that have this, right? So she picks a random sample of 160 trees and examines them, and 48 of them are infected. So hopefully you can see that that's actually a p-hat. So that's 48 over 160 had the disease, okay? Find the 95% confidence interval proportion. So this is actually pretty easy. So we know what we do here is we go p-hat plus and minus. So this is interesting because I want to talk about this down here. So for the proportion of trees, okay, so we're going to go p-hat plus and minus 1.96 square root p-hat times 1 minus p-hat over n. And obviously we'll sub in our n being 160 here, so I'll sub that in, and as we know with our interval here, so I'll pause the video and sub this in. Okay, so I've that set up in my calculator. So again, it says 3 significant figures. So as I've said before in previous videos, if you don't know the difference between decimal places and significant figures, to have a look at it up. So you're kind of lucky in this question because significant figures and decimal places both give the same kind of answers. They're both 3 decimal places. So then this is 229. Okay, and then as a percentages, that will be 37.1% is greater than P, and then P is greater than 22.9%. So that's what we, just because this ties in with what part 2 is here, okay? Explain what this means in terms of the question. So what this means is we are 95% confident that the true proportion, the population proportion of trees in this forest that are infected with this disease is between 37.1% and 22.9%. So you can rewind that back to see what I said there rather than me spelling it out here. But the key thing is that we are 95% confident that the population proportion of trees with this disease is between this value and this value. Okay, that's what this interval means in context of the question. Great, so I'll scroll along here. So I think this is a relatively short question here. So I think there's a few, yeah, so there's 2 things here with the curve. Let's see, can I zoom out a bit so I can get both in on the diagram? That we can do it. Okay, so everyone should pause the video and have a go at this. See, can you get it done? Okay, so hopefully you gave that a go. So the diagram below shows a normal curve. Indeed it does, and it has a mean of 360, which it does. On the same diagram, draw a new curve that will have the same standard deviation with a new mean. So you got to understand that standard deviation is a talk about how spread out you are, okay? Standard deviation is spread, and mean is like a location of where your center is. So what we want to do is we want to keep the exact same spread on this here. It needs to look the exact same shape, but it's not got to not be at, it needs to have its peak here at the 350. So that looks like this. So it keeps its exact same shape and just comes over like that. So it's the same amount spread out from the pink line, its new mean. So that would be full marks there, okay? Okay, so what do we got down here? The diagram shows below the normal curve again. On this diagram, draw a new curve that will also have the 360 mean, so it's still on the mean, but it will have a smaller standard deviation. So that's a code word. When you see smaller standard deviation, it means less spread out. Okay, so it's less spread out. That's what that means. You're less spread out from who? You're less spread out from your mean. So basically, this thing's going to get skinnier. And because it gets skinnier, it also has to get a little bit taller to fit all the data underneath it. So you would just draw something like this for the examiner. And you get your marks, okay? Try and keep it symmetrical as well. So they're just checking to see if you understand that smaller standard deviation means less spread out. So you draw something that's narrower around the mean. And then also they're testing to see if you made it a little bit taller because you still got to fit all that data underneath it, you know. Because these are histograms, these are bars, you know, from a histogram, so the data still has to fit under there. Hopefully that makes sense to people. So that's a fun question there. Nice, easy one. All right, I'm gonna pause this, scroll along to our next one. Okay, great. So I found our next question here. So this, just so people who are following along, they're interested in the years. This comes from 2023's paper, and it's just a kind of little standalone thing. We don't need anything from previously in the question, so I recommend people pausing the video and giving this a go, seeing can you get it out. Okay, so what they're telling us is there's some national newspaper that done a survey of N teenagers, so N is unknown. 35% said they play this online word game. So that in a way is a p hat for people. We've just read a p hat. That is from a sample. Based on this, a 95% confidence interval that goes around p as we know was constructed as accurately as possible. So that means when they say as accurately as possible, that's code word for saying they use this formula. Plus or minus 1.96 p hat 1 minus p hat. The non-accurate way of doing that will be going p hat plus and minus 1 over the square root of n. That's the less accurate formula, okay? Just so people understand, they could examine that and see what they mean. Part one of this could have been explain what they mean by as accurately as possible, and it will be literally what I talked to you about there. Correct to one decimal place, this is what they got, okay? So work out what n was, right? So how do we do this? So we got to kind of work back to what they've done here. So remember, this is the thing that we go plus and minus, okay? So this thing must have been plus to the 35% to make this number here, right? And it must have been minus away to make this number here. So we can just work out what the plus or minus thing is as a decimal. So you just go like 43% as a decimal, 43.5%, take away the p hat, which is at the center. Hopefully this makes sense to people. So this is what we call the radius of the confidence interval sometimes. So that works out as 0.085. So what we've really gone here is plus and minus 0.085 onto our p hat, which was 0.35, right? So we just basically set this equal to this down here, and then we work out, we move it around to find n. So I don't know if I've already done one like this, but we're doing it now anyways. So we have 0.085 equals 1.96 square root p hat, which is known in the question, so it's a nice number of this, 1 minus 0.35 over n. Now we're looking for n, so n is an unknown. So here you go, one equation, one unknown. So let me show you how to move this around. Bring this underneath here, divide both sides by 1.96, and then square both sides. So I'm going to do that 2 goes in one go. It's a straightforward move. Square, and then you've got the 0.35 here. You can use as many steps as you want, you know, whatever you're comfortable with. Over n. So I'm going to show a pretty slick way of doing this here in one go. So I'm going to multiply up by the n here, and then I'm going to take this whole thing and divide it underneath here. So in one go, n can be written as 3/5, 1 minus 3/5. N moved up here, this thing moved underneath then. So hopefully that makes sense. But again, if it doesn't make sense, you know, you can just use more steps. But that looks really good there, because all I need to do now is use the calculator once, you know. So that's good for me, and it's good for the examiner who has to grade it. And if I did make a mistake, it's easy to look back over my workings to see did I move something incorrectly around, you know. So I'm getting that to work out as 120.96. Now that's pretty close to 121, so I'll probably just round it up. Yeah, so we don't they don't give us enough information here to say should we be rounding up or down. So just the way this question is set up here, because this is so close as well, we just write 121, you know. It's good enough. Okay. Yeah. So there are some questions where you do have to pause and think, do I round up or down? But for this here, we aren't given any information of whether or not we should be like just below this value or just above it. Okay, that kind of thing. Hopefully that makes sense. Great. So that's that done. I think that's its own kind of standalone question from that year. So then we move on to this other type of question here, which is looking at speeds on a certain road. Okay, and then I have a note here to discuss p-values. Now, actually, in the part one, I done a pretty long discussion on what p-values are. So if you want that long discussion, I recommend going back to the part one of this tutorial series on inferential statistics past paper questions. But I'll still have a short discussion on it down here when I have to answer this part two. Okay, great. So let me zoom in a bit here and we'll try and get these questions answered. Okay, the speeds of 150 random cars, so they've kind of given us an n there. So we're probably going to be talking about x bars here, you know, we're not going to be talking about individual speeds. We'll see anyways as it goes on. So the mean speed of the cars from the sample, that's what I'm kind of reading here, was this, and it had this standard deviation. And this is the speed limit on the road. So that might be a mu here. We might be testing that. And that's what they're getting at here. Test at the 5% level of significance that the mean speed of cars passing the checkpoint is greater than the speed limit. Okay, so that's interesting. Is greater than the speed limit. State the null hypothesis and the alternative hypothesis. Okay, so right, and it's interesting that they say greater than here. So we need to somehow get this into our H0, H1. So H0, this is from a mock paper as well. So we might discuss something about that in a sec. So H0 here would say, because we're testing whether or not you're greater than the speed limit, H0 is this conservative statement. It doesn't want things to change. So it will want the speed to be still 112. You know, it wants people to be following the speed limit. It wants there to be no change from this, okay? Whereas this one won't want this. And rather than it being this isn't what they said in the question. They don't want it does not equal 112. They're actually very specific here. They want to check if it's greater than 112, okay? So when we normally write the mu does not equal 112, that's what we call a two-tailed test. But here we're doing like a one-tailed test, where we're just checking if it's above. Okay, hopefully that makes sense to people. But the standard in the state exam questions is that you're always dealing with the two-tailed test. In other words, you have two rejection regions. Okay, as we know, this is our 1.96, so our minus 1.96, and if you have a z-score below here or above here, you get rejected, and that's what we call the two-tailed test. But what they're kind of on about here is where they're just interested if you're just above a z-score. So this is not very standard. We're just kind of, there's some z-score here, and we're going to try and make sure that we're not in its rejection region, okay? And this is going to be worth all the 5%, so it's a little bit unusual, this question here. It's because when you have 1.96 here, this size of this area here is 2.5%. And so the z-score can't be 1.96 here that we're testing against, because this area here is 5%. So I'm just going to read this again just to be doubly sure that's what they want, because I don't remember there being too many questions on the Leaving Cert higher level where they want us to be doing these one-sided tests. So one second. Yeah, no, no, it does want one of these. So this, as I said, it's a very unusual question that we'll be working out a z-score and we won't actually be comparing it to our usual rejection values here, 1.96 minus 1.96, because as I said, this is a one-tailed test. We just don't want to be greater than the value, you know. So let's check this out anyways. Let's get a z-score. Everyone feels a lot safer once you work out a z-score, you know, and it is this formula here because we're talking about the mean of the sample size, how unusual it is here, the 115. That's what we're comparing to the 112 over sigma over root n. So then z equals the 115 minus the 112, which is the mu, that's what we're testing, over, it's got quite a large standard deviation, 24, over the square root of 150. But it did have a large sample size. Okay, so let's type that into calculator. 24 over root 150. So I get a z-score here of 1.53. Yeah, remember 2 decimal places we want on that. Okay, so, okay. What we would say straight away here, if this was just one of these standard tests, is, oh, this is less than 1.96, you know? So then we therefore do not reject H0. We're not in the rejection region. But as I said, 1.96 isn't the test score it's not our critical test score when we're doing a one-tailed test like this with a greater than symbol. And I said, these are unusual. So it's nearly good for you to have seen one of these in the video. But I don't think they're going to come up that much in a state exam. So that's why this is a mock. So we need to find out what our new critical Z-score is here. So we're actually going to have to go to the tables book for that. I think we've already seen it earlier on today. It's a Z-score that has what size area below it? So it's going to have 95% of the area below it if it has 5% above it. So if we go and we look at the tables book, remember we had this from earlier today. The one that has 95% below it is 1.645. Okay. So that's 1.645. So this critical z-score is 1.645. So that's our critical z-score. If we are above that z-score, we're in this, which is called the rejection region for a one-tailed test at the 5% level significance. Okay. But again, he gets away with it here. This is just below the critical z-score. So we're not in the rejection region. Not in the rejection region. Okay. And because we're not in that red rejection region there for a one-tailed test, we do not, so this is our conclusion then, give your conclusion, we do not reject H0, okay? We do not reject them. And we would say at the 5% level of significance, we do not reject H0, which means that the average speed limit on this road is still being followed. It's not above. It is not above 112. It is less than this. What you could say as well here, it's not so much that this was to be equal to this. It's that this was to be less than. So that's actually a more technically correct thing. That they were following the speed limit. So in a one-tailed test, you're really just testing are you above a value or below it, not so much as you are equal to it. So that's an important correction there for that. So yeah, so that would be our conclusion. We do not reject H0, which means that the average speed of the cars on this road is actually below the speed limit. It's not greater than the speed limit. So a little bit of an unusual question there because it was one-tailed. Hopefully people are okay with that. Yep, so let me clear that away. Yep. Find the p-value for the mean speed of cars passing the checkpoint. Comment on what can be concluded from its value in a two-tailed test at the 5% level of significance. Right, so now they're changing things here. So then this is your classic mock thing. So this here was properly done as a one-tailed test, but now then they're on about it being used as a two-tailed test. Okay, so let's work out a p-value using the two-tailed test formula, which we know from earlier on if you watch the part 4. The p-value in a two-tailed test, a p-value is an area, first of all, as we previously discussed. And we go 1 minus the probability that z is less than the modulus of this test score, we can call it z1. Okay, and our z1 there, our test score was, what was it, 1.53? So what this is getting, the reason there's a 2 there, bringing up our discussion on p-values again. This is a 0 here. So we get our test score, which was 1.53, but because we're talking about a two-tailed test now, it also has a -1. So there are two regions here. And the p-value that's associated with this is literally just the area of these two guys added together. Okay, and that's why we're doubling a certain area here. And the modulus is here if you're dealing with the -1 to just work with the +1 basically. So then this is 2 times 1 minus the probability that z is less than 1.53. And then this is equal to, I can read this from the tables book, what's below 1.53? It's this number here, 9370. So this is 2 times, this will be your workings, 1 minus 0. What was it, 9370 was it? 9370, yeah. 9370. So definitely a bit of a complicated question, this one. 2 times, so this is going to be an area we're going to get, because that's what a p-value is, it's an area. So as an area, this was 126, okay? 0.126. And so what's the conclusion on that? So again, your conclusion was this here is greater than our level of significance, which was 0.05. So that means we therefore do not reject H0, okay? And so if you were, that is the lowest level of significance at which you begin to reject H0. So basically, if we were doing 15% level of significance here, we would be rejecting H0 because our p-value was less than it. So again, I done a long discussion on the p-value stuff before, so hopefully people are good with that. So find the p-value and comment on what can be concluded from it in a two-tailed test. So again, the conclusion is we do not reject H0, as in the speed limit is not different. The average speed of the cars is not different from the speed limit here. There's no difference. Okay, because we're not rejecting H0 here based on the p-value. Okay, so hopefully that makes sense. Let me clear that away, get on to our next question. Oh yeah, so I was just scrolling along here looking for the next one. So it turns out there's a very interesting part 3 on this question. And it says then, this will be linked to the part we just done before there. It would be find the smallest sample size for which this result could be regarded as significant. Now I think I actually done something like this before with people earlier on in this. Remember when I was changing the size of the root n? I forget what question it was on, but basically when you have your z-score formula here, x bar minus mu over sigma over root n, and say if, I think the question was where the z-score worked out as minus 3.7, you'll remember it better because you can rewind the video, and I think the sample size was something like 120, and I reduced it down to 20, and then we were no longer rejecting H0 because we got the value in below 1.96 for a two-tailed test. So that's what we're kind of doing here. We're kind of finding the smallest sample size for which we'll actually start to reject H0 now. So if we remember some of the values from the question, I can scroll up if I forget some of them. I think we had a 115 was our x bar. We were comparing it to 112. I think sigma was 27, and then this is unknown now, okay? So before this was only working out as something like a plus 1.53, I think it was. So what we're going to do now is we're going to set this equal to 1.96 so that we enter a rejection for a two-tailed test. Now they're not very specific here, but as I said, this is a mock exam, so we'll kind of default to what the natural thing is, which is treating it as a two-tailed test. So we set it to this, whereas if it was the one-tailed test, we'd be setting it equal to the 1645 that you remember from before, okay? The 1645 for a one-tailed test. So hopefully that makes sense to people. Anyways, so we want to move this around. There's a few different ways you can do the algebra on this here. This is obviously pause the video, give it a go. One nice thing you can realize is when you have a fraction on the bottom, that root n actually belongs on top. So this is one quick way to do this. So that root n, it's really root n multiplied by 115 minus 112 over 27 equals this 1.96. And so in one quick move here, you can just get the root n on its own. Root n equals 1. And of course you can just, use multiple steps here if you don't feel comfortable moving things around like this. But this is the great place to get if you can do it. And then you want to just square both sides then, and you get your n. So let's find n here. So and we might have to have a bit of a think of whether or not we round up or down. 115 minus 112. 115 minus 112 over 27. So n there for me is working out at about 311.17. Okay, so I said I'd just put in here for anyone who's following along. I'll let you back to the video in a second. So when I took this down, I remember I made up 27. I said the number was 27. But if you read the question there previously, I took this down wrong. So this was 24. Okay, so when you're moving this around, what you'll get here is a 24 down here, and then this number here works out as 245.86, and so the description you're going to get over here about whether you round up or down, basically what I do with the incorrect number here, 311.17, you'll do the same with this number, and you should get something like, you'll do the same where you kind of round up 246, but you do that by subbing it back in here and checking, as you'll see in a second, does it go above or below the 1.96, okay? Great, so I'll let you back to the video. So just correcting that there for anyone who's following along. Now we have to decide whether or not we round up or down. So when it regards as significant, we're really looking to reject this guy, okay? So we want this thing to actually be greater than 1.96. So we wouldn't want it to be like 1.95 because then that's not significant. H0 got to live there, you know, he survived. So we want this significant thing. So we want H0 to lose. So we want a value that's going to come out of the thing I circled in pink here as bigger than 1.96. So you have to test both values here. And you need to show this for the examiner. There's two options. It can either be 311 rounded down, or it can be 312. Okay? When it's 311, when you sub it back in here, right, let's do that. 115 minus 112 over 27 over the square root of 311. I get this value. This works out as 1.959, and that's not good enough. That's not significant. We wouldn't be rejecting H0 there. So it must be the 312. When I put the 312 in, that just gets us slightly over the 1.96, which is what we want. 26 there. So this is our guy. This is our guy. This is not our guy because then this isn't significant. We didn't get into the rejection region when we had a sample size of 311. Okay, so hopefully that makes sense to people. That's a really good question there, the part 3. So you can see changing the sample size actually can change your conclusion on whether or not you reject H0 or not, you know. Great. Okay, so let me clear that away and move on to our next question. I don't think there's another part to this one. There isn't. Oh, but our next question is actually just here. So yeah, I think I just have there's not a whole lot on this one, but we will do it. The reason I highlighted this one is because this is from 2022. It talks about the more accurate formula, and I've already kind of done a discussion on this so far, but I'll just do it again. When you're using this formula, which is known as the less accurate formula, you go p hat plus or minus 1 over root n, and then the part 3 here wants you to use the more accurate formula for your 95% confidence interval, which is plus and minus 1.96 square root p hat. And you're meant to know all these formulas off by heart, of course, because you use them so much over n. So that's the more accurate formula. And obviously you'll get two separate intervals. They'll both have p in the middle like this. There's a slightly different value, you know. But whichever one was calculated with this formula is the more accurate one, okay? Okay, hopefully people are okay with that. There's probably no need to do that. I've kind of commented on this being the more accurate one and then this being the less accurate one. Okay, great. So I'll pause and roll along here just to see. Yeah, so let me pause. Yeah, okay. So I've scrolled along here now to 2022 mock paper. So this is a good question because this revises a little bit of what we just talked about there a second ago, which was how you can change the sample size to make a result significant or not significant. In other words, you move in and out of the rejection region depending on the sample size. So you see here, it says show that if you had a sample size of 100, you're a significant result. And then this part 3 is very similar to what we just done a second ago. Find the smallest sample size that you then start to enter the rejection region. Okay, so hopefully you can kind of pause the video and give this a go to see if you learned something from what we talked about there previously in the previous question. So pause the video, give this a go. Right. The mean percentage mark for candidates from the 2019 Leaving Cert for maths was this, with that standard deviation. So there's a bit of spread. The suggestion that candidates who appeal their results have on average similar results to all others, okay, is being investigated. So they're checking if people appeal, does their mean mark change. So we then took a sample of, so this we're comparing sample means here, so we're going to probably be using this formula here, unless there's something, we're going to read something very unusual in the next line or two, which I don't think so. A random sample of candidates who appealed is taken. The mean percentage mark of this sample was that, so that is an X bar. Okay, so we definitely will be using this formula down here, and we can keep it in percentage. There's no need to change it to a decimal because our sigma will be in a percentage as well. Okay, so show that if you have a sample size of 25, this is not significant, right? Let's do that. So this will be a two-tailed test, like all our tests are usually, not that unusual mock one from before where it was one-tailed. So we go 67.5. So it is clearly higher, but is this going to be significant? We have to check with the formula because the mean of this sample is clearly higher than what the overall mean is of the population. Okay, so then we have 16.4 here for sigma over root 25, which will work out as a 5. So we'll work that out. 67.5 minus 63.3, 16.4 over root 25. So there you go. You're only getting, what are you getting here? Z is equal to 1.28, and that's definitely not significant. Okay, that's well below 1.6. So this is what we call not significant. So we would be do not reject H0 here, where H0 would be that mu is still equal to 63.3%. So in other words, there's been no change. H0 is the no change guy. There's been no change from the mean. That would be our conclusion. Now it says, show that if the sample size was 100, that you will have a difference. There will be a different conclusion here. So let's do that. Z equals 67.5 minus 63.3 over 16.4 over root 100 now. Okay. And we're going to get a different Z score. We get a pretty big Z score. We get 2.56, which is greater than 1.96. So that is significant. That is significant enough now at the 5% level of significance. So you would have to state this as well. At the 5% level of significance, that's where the 1.96 comes from. At the 5% alpha, alpha stands for level of significance. Here we would reject H0. Okay. And what does that mean? That means that mu no longer equals 63.3%. So therefore, the conclusion would be, in basic words, is that people who appealed the results on average got a higher result than those who didn't appeal. Okay, so hopefully, or well, basically, it's not so much that it's higher, but they got a different average compared to the original population state exam for everyone. Okay, so you got to be careful with rather than saying it was greater than, because then that's the one-tailed test that we talked about earlier on. Okay, so okay, hopefully people are good with that. Right, let me clear that away. And so the next question here is obviously what we dealt with before. So we're actually looking for the specific n that makes the thing rejectable, H0 rejectable. So what you do here is you basically set the Z score equal to 1.96. Your X bar is the same as it was before. I kind of forget the values even though I had them there a second ago. It was 67.5 in for X bar, 63.3 in for mu, 16.4 in for this guy, sigma, and then this is the root n which we're looking for. So again, I'm going to move that around. I already showed you just a second ago how to move this around. So let's see how to do it again. So the root n's up there. So I think I done 1.96 all over this thing. Obviously you can move this around in steps. You don't have to be doing crazy stuff like this, moving it all around in one go. So as I said, that root n really is on top. So I just fired all of that under the 1.6 and then I squared everything. Cool. So let's get an n here. So this is identical to what I just showed you before. You know, this is me solving a duplicate problem, you know. You've already learned this before. So this was a kind of an opportunity to test, did you learn it and were you able to try this out yourselves, you know. 16.4. That looks like an 8, but it's a 6. So n here works out as 58.57. Again, it's not just a matter of round up or down. You need to test this. This can either be 58 or it can be 59. And you need to put both of them in here and see which one makes it above 1.96, because then you become significant. Then you become able to reject H0, which is what they're on about with this, is significant. So let's put the 58 in there. Takes a little second, this 63.3 over 16.4 over root 58. And when you put root 58 in there, you get 1.5, which is not going to be good enough, okay? That's not going to work. If you put root 59 in, though, for n, you get 1.967. And that's all good, because now you're in a reject. If that's your z-score, that's good for rejection. So that is a significant result. So the answer is 59. So you round up. So again, hopefully people learned from that. You've seen kind of a double dose of how to do that question. Okay, so let me scroll along here to our next question. Let me pause the video. Okay, so I scroll along to this one. So noticing the video's on like 53 minutes now. So what I'm going to do, this will be the last question in this part of the video, and then the next part we'll continue on with the document. So I said I'll do this one in this part of the video because we've done a lot of talking about p-values so far in both the part 1 and this part. So we'll do this one here. So it says here, this is obviously gets you to get the z-score in part 1 and then gets you to get the p-value here. So let's see what's going on. A news report claimed that 6th-year students in Ireland studied on average 21 hours a week. Okay, a leaving cert class. So we've got a sample now of 60 students. So they're going to have an X bar of their own. It was found that their X bar was this. So we want to see if that is significantly different from what the mu is for the country, 21. And we got a sigma from the sample of 5.2. So what we do is we don't know what the sigma is. They didn't state it here for the country, but the best estimate of sigma, if we don't know what the population sigma is our own sigma here from our sample. So hopefully that makes sense to people, that you've heard something like that before. Anyways, z equals x bar minus mu over sigma over root n for this question. So z equals the 19. So it's clearly less, okay? But we got to see if it's significant or not by comparing it to the plus and minus 1.96. Are we in the rejection region or not, 5.2 over root the all-important n, so that was 60. So then the z here works out as 0.98 minus 21 over 5.2 root 60. I typed that in there correctly, didn't I? Yeah, 21. So 19.8. So when I type that in, I get a z-score that is not significant of 1.7 rounded to 9. So what you would state here is as minus 1.79 is this here is actually greater than minus 1.96. Okay, we therefore do not reject H0, which means it's not. It's another way of saying it's not significant. But you'd say that at the 5%. This is for a two-tailed as well. So when you're talking about a two-tailed test, that means we're looking at the 1.96 as our comparison guy. Okay, that's our guy for a two-tailed test. And most of the tests are always these two-tailed tests, unless you get the unusual mock one we dealt with earlier on, which was only one-tailed. Comment on what can be concluded. So basically, we have a not significant result here. We didn't get into the rejection region with this z-score, and we're going to work out a p-value for that in a second, and then we're going to have a nice little discussion on the p-value. So what you would say here, we'll just make the comment based on the z-score first. And what this means is H0 doesn't get rejected. So what H0 means is that this is still correct, that mu equals 21 hours, okay? So then on average, 6th-year students in the country still do study for 21 hours a week outside class, okay? And that'll be full marks. Now we've got to get a p-value. What did I tell you earlier on? P-value is just an area, and it just follows this formula of 2 times 1 minus the probability that z is less than the modulus of your test score. Call it z1 there. So the test score in this question was, now this is a good one because this is a negative one. So we will be using the modulus here to turn this into a positive. So the p-value equals 2 times 1 minus the probability that z is less than 1.79, okay? Like that. So you see the modulus worked for us there in turning that thing positive. Great, so we go to our tables book and see what's below 1.79. Scrolling across here, you see it's this number here, 9633. You have your own tables book anyways, you can do that to confirm. I got 9633 if I remember correctly there. So this is 1 minus 0.9633. I'll just recall it correctly here, 9633, yeah. So then that's 2 bracket 1 minus 0.9633. Now before I call out the answer, for anyone who didn't do this, let's think about it. We did not reject H0 here. So should this p-value be above or below 0.5? Just think about that for a second. Pause the video and have a think about it. If you're not rejecting H0, should your p-value be above or below your level of significance of 5%? So hopefully you realized it should have been above if you're not rejecting H0. Okay, so p-values that are bigger than the level of significance, you do not reject H0. They're what you'd call not significant. Okay, so as I wrote earlier on for people, what the p-value is, it's an area first of all, but it's this here. I'll write this I talked about maybe in the part 1 of this video. It's the lowest level of significance. This is a good place to end this video. Significance. I'll just write it as quickly as I can. Lowest level of significance, and the level of significance is called alpha. We call it alpha. Okay, alpha looks like that. It's the lowest level of significance at which we begin to reject H0. Okay, we begin to reject H0. So remember, this was the level of significance here was 5%, and the p-value was this. So we don't reject H0 because this was our level of significance. But this is the thing, right? There's other types of tests that you can do. We don't do them on the leaving cert, but there are what we call this 5% comes from when we're dealing with 95% confidence intervals, but there are also 90% confidence intervals. And when you have 90% confidence intervals, the level of significance is 10%. And at a 10% level of significance, if alpha was 10%, not 5%, this p-value would result in H0 being rejected, okay? So that if alpha was 10%, we would reject H0 for this p-value, right? But if alpha is 5% like it is in this question here, right? We do not reject H0. It's not significant enough. So hopefully that's making sense to people. So if alpha was exactly 7.34%, that is the moment when we start rejecting H0. So it's like the turning point for H0. If alpha is 10% level of significance, and this was your p-value, H0 gets rejected, right? If you have a safe 5%, it doesn't. So if alpha was 7.34 exactly, that's when you just get to reject H0, okay? So hopefully that makes sense to people. I know it looks messy on the screen. It definitely looks super messy. But hopefully I was able to walk you through that with my voice and you were able to tag along with it. So video's on an hour now, so we'll end it here, and I'll actually scroll along to see where's our next. Yeah, so we're gonna pick up the part 3 of this on this question next. Okay, so hopefully that was helpful for people, this part of the video. Okay, so we're going to pick up where we left off in part 2 for this part 3 of important past paper questions you should know on inferential statistics. So some pretty easy ones to start us off here. So obviously pause the video, give them a go yourselves. So you're asked to explain the significance, the relevance of these two z-scores when we're talking about the normal distribution. So to be honest, you'd be waffling a bit if you didn't draw a diagram to explain this, okay? The diagram actually answers the question pretty much. So the reason these are pretty relevant or significant is because between those two z-scores, what's the area? 95%, okay? So that's why, because, and then all the kind of confidence tests we do are usually 95% or at the 5% level of significance. So they mark the beginning and the end of our rejection region, okay? So that's pretty important there. And if you want to put that into a compact statement, the probability that Z is between plus 1.96 and minus 1.96. Oh, minus 1.96 is equal to 0.95. Okay, but sure, the diagram tells us this, you know. But yeah, you'd want just a statement there, you know. We perform 95% confidence interval tests all the time, and then these are our Z scores that bound the region of 95% confidence. Okay, cool. Trans-Sky Airways surveyed 2,500 of its passengers about a new service it proposed to introduce. The variable p hat is the proportion respondents who said they would use the new service. Okay. Now you've heard me say this term before, this radius of the confidence interval before, and you need to know what that means. So I've already said that when we're doing confidence intervals for proportions, 1.96 square root, this is our formula, we need to know it off by heart, p hat over n. This here is known as the radius. That's what we would call the radius. And it basically just tells us straight up that this is the radius here. So this green thing is 0.1568. Okay, so that's just really a mathematical instruction. We just got to go do some algebra on this now. So let's give this a go. So yeah, 1.9. Let me see, can I make this a bit neater here? So let me clear this away for a sec and pull this up. It'll always look a bit neater when there's the white background, you know. So yeah, coming up here, solving this problem here. So it's more so, as we said, it's the radius. That's the radius there, and then that's equal to that number. So then we have 1.96 square root. Now, we don't know the p hat. The p hat is the unknown. Now, you can actually call that x if you want, but just tell the examiner that that's what it is, you know, because x is a nicer symbol to show as our unknown. 2,500 was the sample size, and this is equal to 0.1568. But you can, of course, call it p hat if you feel comfortable moving that around. Right, so this is obviously going to give a quadratic, so let's do a few blunt force moves. So we're going to divide by this thing, then square everything, and then multiply across by 2,500, okay? So I'm going to do loads of moves in one go here. So I'm actually going to multiply the inside of this out. I'm going to bring the 1.96 underneath this. So, but obviously, if you're not comfortable doing all these moves in one go, don't do it. Overexert yourselves. So I brought the 1.96 under this, got rid of the square root by squaring everyone, and then I multiplied, because this there's no square root anymore, so I just multiplied both sides by 2,500, and so there's a 2,500 chilling here. Okay. Obviously you could split that into a few different steps, but I'm sure you paused the video and given this a go, you know. So that's just a number there, so I'll bring that over into my quadratic. So I have x squared, and then whatever this number is, minus 2,500 bracket 0.01568 or 1.96 squared. Oh, it works out quite neat. It's actually just like 0.16 equals 0. Now I'm actually going to keep it as a decimal, like that, because I'm just going to use the quadratic formula here. I'm not going to bother trying to factorize it as a fraction and multiplying, you know, tidying up. I'm not going to. So I'm just going to use the minus b formula on this. So then the x that we're looking for, which is the p hat, is going to be minus b, which is 1, plus minus square root of 1 squared, which is just 1. So it's minus 4 bracket 1 bracket c, which is minus 0.16, all over 2 times a, which is 2. So I'll type that into your calculator. I'm sure you can all type that kind of thing into a calculator. 1, so it's basically plus 4 by 0.16. 0.1642. So have I typed that in correctly? Let me make sure I have everything all good. I'm getting a bit funny answer there. Yeah, so let me see if I done this correct. One sec. Ah, yes, I see the error. So the error is here, when you multiply this out, you get x minus x squared. Okay, x minus x squared. But sure, you probably seen that anyways. So that's x minus x squared there. And so when this comes over, realistically, this is minus x and a plus x here. But you can still use the minus b formula on this, so you just got to be a bit careful So then this is going to be minus b, which will turn to minus 1. This will still be 1 squared. And then this will be 2 times a is minus 1, so that's a minus 2 there. So let's update that. Okay. I think that's all good now. Let me see if there's any other little hiccup. There is one other little thing here. So if my a is minus 1, I need to put a 4ac in there. So if I put the minus in here now, this should give me a reasonable answer because we're getting funny answers otherwise. So I was like getting numbers bigger than 1 for p hat, which is not possible, and then I was getting numbers less than 0, which isn't possible. So this is possible now. So x is 0.8 there, or x is 0.2. Okay, so there are two reasonable p hats, and it says p hat is supposed to be between this and this, so then that will be the winning p hat there. Okay, because x is p hat, so then p hat for this question is 0.8. Now it shouldn't be anywhere near as tricky as I made it there by not multiplying this thing out correctly and then having to use the minus b formula with the minus in front of the x, not having multiplied everything by minus 1. But yeah, like I don't think that was too hard of a question. I'm sure everyone was able to pause it and kind of get through it. At the end of the day, this was the tough step here in red, which was writing the radius equal to what they tell you the radius is. And look at it, you have one equation, one unknown x. So it was all about finding x there. Okay, right, I'll clear that away, get on to our next question. So let me pause and scroll along to it. Yes. So this is the very important question here now. So this was a pretty tough one they came up with here in 2019, right? And the reason it's what I would class as like being really tough and really mean is because we're kind of in a bit of a default state that whenever we see an n in a question, we always use this z-score formula. Like if ever we see an n floating around in a question, it's like, oh yeah, our z-score formula requires this version. But as you'll see here when you do part 2, that's not the case, okay? So I recommend everyone pausing the video and doing both of these out, okay, and see how you get on. Right, so let's read this carefully. There's a motoring magazine, collected data on cars on a certain stretch of road, and they had a sample size here of 800, okay? The ages of the cars were recorded. 174 of them were new. Construct a 95% confidence interval for the Porsche cars. Right, that's not complicated, right? So I'm sure we can all do p hat plus or minus 1.96 square root p hat 1 minus p hat over n, and where your p hat there is equal to 174 over 800, and the n equals 800. So I'm going to just sub that in here and we'll write our confidence interval, okay? Because we might need it, because this is like a part 1 and a part 2, okay? So I'm going to pause the video, sub that in. Great, so I've typed that into my calculator. Obviously, to get marks off your examiner as well, you need to show yourself subbing it in like this. So I paused the video to do that because it's fairly straightforward grunt work. So when you put that in with the plus, you get 2461 to 4 significant figures. Again, if you don't know the difference between significant figures and decimal places, you definitely want to go on YouTube and find someone to keep walking you through that. Okay, so there we go. And it says to give them like that in decimals. It doesn't say anything about percentages. So what this really means, it's like 24.61%. And then this is 18.89%. So as a percentage, that still is 4 significant figures, but now it's only 2 decimal places. So you really do need to know the difference between them if it's asked in a question, Right, so that was easy. That was the gimme. Now the part 2 was not. The part 2 is tricky, okay? The data on the speeds, now we're talking about speed data, not how old the cars are, right? So we might need this stuff in red, okay? The data on the speeds of the 800 vehicles is normally distributed with an average of this, right? So they have sort of told us that that's an X bar, okay? So absolutely, this is a sample. This isn't all the cars that ever drive on this road, okay? That is still a sample, and this is a sample mean, fair enough, okay? And the sample had this standard deviation. You were then asked what proportion of cars on this stretch of road would you expect to find traveling at this speed? Now, what's not cool about this question, you might say, is that, okay, well, we do have this is n, so why don't we go and do this, where we go and call this sort of our mu, and then this are X bar, okay? But that's not what we're doing here. This isn't an X bar, okay? What this is, we're just asking, what proportion, what's the chance of a car traveling at this over this speed, okay? So that's like an individual X value. That's not an X bar. Okay, you got to read that carefully. So they're really just asking you within this 800 sample, what proportion we're going faster than 95 kilometers per hour. So it's really, we're just asking where does this individual value compare? So in a way, this 800 becomes the population, okay? Because we're kind of living within this sample size comparing a value. So this is a really mean question because a lot of students, whenever they know there's an n in a question, they just sort of default to, oh yeah, let's use this formula, When realistically, in this actual formula here, what we're meant to be doing is going x minus mu over sigma. Now, kind of a bit of a fair thing here in this question, okay? A lot of students would have went and done this and they'd have gotten a silly value, okay? So let's actually work out that silly value. Let's go and let's assume this isn't the correct way to do it. This is not an X bar, but let's put it in for a second. And then let's assume this is a mu, which um, it will be, but this isn't an X bar. So this is 87.3 over sigma, which was 12, over the square root of 800. Now, I'm sure you've all paused the video on how to go doing this and arrived at this value. And you should see it's a bit over the top, as in it's very, very big. So yeah, that number is working out as like 18, okay? So you should know something's really wrong there. The Z-scores don't usually be that big, They're usually, even your tables book just gives them between 3 and -3, So there's something very wrong here. This is like way too rejectable as a value, okay? There's like no chance at all at anyone traveling at this speed, okay? Because this isn't the formula we were meant to use, okay? We're not asking what's the chance of us getting a sample size of 800 cars that had this sample mean when the mean of the population was this, okay? That's extremely unlikely that you're going to get a sample mean of 95 with 800 sampled and it to be so much larger than what the population mean is. So it was never this formula, okay? And I think it's in part 2 of this video, I do an infographic. I bring it up on the screen where I kind of talk about in the sense I regard the sample means as if they were gangs, and then you can kind of see how when there's very little lee room, you have very little lee room if you're comparing sample means to have such a large difference between, say, the mean and the value you're testing, so I recommend going and having a look at that, okay? But yeah, this was a bit of a mean question, but it wasn't too bad because you got such a ridiculous value here that you'd know that there was probably something wrong. And so what a lot of people would have done in this state exam year, they would have like, okay, this is ridiculous, so I'm going to use the other formula. Okay, and that would have got them the marks. So Z equals, we're testing this 95 here, and we're going 87.3, and we're going over 12. And we get a much more respectable Z value here when I type it in. 95 minus 87.3 over 12. Yeah, and you get a Z value there, which is much more reasonable of 0.64, okay? So what are we meant to actually do in this question? Let me rub away some of the stuff that's not to be used in this question. So let me rub away a lot of these markings here too. I'll put this over here, and then that's our Z-score. So what this question actually asked was, as I said, this here is really an X value. So they're asking what proportion of cars, in other words, an area from the bell curve, what proportion of cars do you expect to be traveling over this speed? So we're looking for the probability that X is greater than 95, right? We just converted this X into a Z-score, so now the question is, what's the probability that Z is greater than 0.64? And what you always got to do when you're looking for areas like this is you want to plot it on the bell curve, both for you and for the examiner, so you know what to do. That's a 0. It doesn't have to be super to scale, so you can just put your 0.64 wherever and shade in the region you're looking for. If you get the area of that green section there, you've got your answer. Now your tables book will not tell you what's above a Z-score. Your tables book will only tell you, for example, what's below 0.64, okay? So how can we do this? Well, the total area underneath the curve is 1. So what we can do is we can get this blue area, take it away from 1, and it'll give the green area, which we're after, which is the probability that Z is greater than 0.64. So that's what we do. We go 1 minus whatever the blue area is, and that's the probability that Z is less than 0.64. Okay? And we can just read that value from our tables book. What's less than 0.64? 7389. Let's see if I can remember that number. This is 1 minus 0.7389. Okay? And that's equal to 389. So there's a 0.2611 probability that a car is going above 95. So they asked what proportion of cars. So it's 26.11%. Okay, is the answer. But you could also, you'd probably get full marks for that. That's the way I'd probably leave that. But because there was only 800 vehicles, we can actually work out how many vehicles there were. So we can just go 800 multiplied by 0.2611. And we see that there'd be something like 208.88 cars. So roughly, it's about 209 cars out of the 800 cars would be traveling over that speed limit. So hopefully that makes sense to people. That's a pretty important question, that one there, where you're giving an n and you're actually not supposed to use the z-score formula that has the root n on the bottom, and it's tricky. They're very rare, these questions, but it was nice, this one, because the z-score was really stupid when you put the root n in, so it was a hint to not use the one with the root n. Okay, great. So I'll clear this away, get our next question set up. Okay, so scroll along. This is continuing talking about this kind of 800 drivers and the speed limits and stuff. So this is a part 3 of this same question. A driver of a car was told that 70% of all the speeds recorded were higher than his speed. Find the speed at which this driver, was driving, and then round it to the nearest whole number. Right. So what we've got to understand is this guy's driving pretty slow, and 70% of all the people are faster than him. So you've got to convert this statement. They've given you an area there, believe it or not. They've given you an area. They're telling you that this guy, if he's a z-score, he'll be some negative z-score, right? And then all the people that are above, there's actually 70% of people are above him. So that area there is 70%, okay? Or 0.7. So hopefully that makes sense to people. We got it. That's how we convert this information here. They're telling us that 70% of people are at a higher speed than him. So this is him down here as a z-score. So we need to somehow find out this z-score. Now our tables book won't tell us about negative z-scores, but the idea is everything is symmetrical. So if 70% is above this negative z-score, then the equivalent positive z-score will have the same 70% below it. Okay, that'll be the same 70%. So that's how we do it. We're going to read off what the positive z-score is that has 70% below it, and then change its sign, because then that z-score would have 70% above it, which is the one we want. So go to our tables book. Who has 70% below them? So you see it's kind of in between this value here. It's a bit annoying, so we'll just kind of maybe pick this one because it's closer to this one. You can do a mid value if you want, but there's no need, You're not going to lose many marks, or you won't lose any marks, you just round it. It's completely acceptable. So we're going to take this one here, and the z-score is 0.52. Okay, 0.52 has 70% of the data below it. So this guy here was 0.52, but that's not the driver. The driver is the negative version of that. So he's this guy here. He is a z-score of minus 0.52. So we know the z-score now. So we'll be able to work out his speed. His speed will be an x value. Okay. So remembering this formula here, I'll write it here. Z equals x minus mu over sigma. We're still using this formula. We've just got the z-score there. It's minus 0.52. We're looking for his x value. The mean, what was the mean here? I think it was, let me go and scroll up so I get this right. Yeah, the mean there was 87.3, and then the sigma was 12. So basically, that'll do it. You got to just kind of get the x on its own here, so you could just move it around here. multiply across by the 12, bring this thing over. So you just show the workings for the examiner here. 12 times minus 0.52 and then plus 87.3. So this guy, this driver speed is, let me do it here. So he's traveling about 81.06. That has units probably of kilometers per hour. I'm sure it's kilometers per hour. So then X, we're told to just round this to the nearest whole number. So he's doing 81 kilometers per hour. And anyways, it's pretty close to 81. So that's that. Yeah, that was a good question there with the areas. It's more of a Z-score question than anything else. So right, I'll clear this away and get us set up for part B. Okay, so part B actually has two parts here. So we're going to get it all pulled up here. And I have a note here to discuss alpha equals 1%. So we should all know what alpha stands for. Alpha is your level of significance. So when we say 5% level of significance, that means that alpha equals 5%. Okay, that's the standard symbol, alpha, level of significance. So we're going to discuss this is a p-value discussion again. I've spoken about p-values quite a bit in the previous parts of these videos. Right, so there's a road safety program that was brought out in this area using posters, signs, and radio. After the program, the motoring magazine done a sample of 100 cars, right? They recorded the speeds of 100 cars. They done it at the 5% level of significance, and they got this p-value. Right. What can the magazine conclude about this p-value? Right, so the idea is that p-value is less than our level of significance. So that's in the rejection region. So just to remind people, I've hammered this out so many times already in the first two parts, but the p-value is an area. Okay, so we have here 1.96 and then plus 1.96. So this region here, if you're in this orange section, you're in the rejection region, right? Rejection region. Now a p-value, you'll get some test score, your z-score that you'll work out in the question, right? And that z-score can then be converted into a p-value. And a p-value is the area outside your z-score. So in this question here, because we should know that this rejection region adds to 5%, that's 2.5% either side. This is standard stuff, we should know this. So that orange region plus that orange region, they're 2.5% each. They add to the 5%. Right. So this p-value is the area outside our test score. So if it's working out as this, that means that the test score must have been out here, right? This is where it must have been. It's either out here or out here. So then this purple area, that is the p-value. Okay, it had to be in the rejection region if you're below 0.05, if that makes sense. So those two purple regions added together, they are the p-value for this question. And they're equal to only 0.24. Whereas the orange region, which is our main rejection region, is 5%. Okay, so we are in the rejection region for that p-value. So what happens is H0 we would be rejecting H0. Okay, so and we do not reject H1. So H0 would be the guy who would say there's been no change. So H0 in this question would have been that there was no change in the average speed. Does that make sense to people? Okay, he's the no change scenario. He would want no change to have happened. And then H1 would say there has been a change, which is what the road safety program would have wanted. There has been a change in the AV speed, average speed. Okay. So basically, because we're in the rejection region, we reject H0. This statement is not true, and we do not reject H1, which means, and then our conclusion is at the 5% level of significance, there has been a change in the average speed on this road. Okay, so in other words, this road safety program did work. Okay, hopefully that makes sense to people. Now, the reason I have discussed alpha equals 1%, we're going to talk about the p-value here again. So, at the 5% level of significance, that p-value meant that H0 got rejected. If we were doing the 1% level of significance, this wouldn't be the rejection region in orange. The rejection region would actually be much, much smaller if it was the 1%. Okay, let me see, can I draw a decent diagram of this? So basically, you would only have a little area out here and here, and they would be adding to give 1%. Okay, this will be your new rejection region. And so if you got a p-value of this 0.24, which I colored in purple down here, okay, remember this then, the purple added to give 2.4%. Okay, so then you're not in the rejection region for a p-value or when the level of significance is 1%. So that's what the p-value is, as I've said before in previous videos, so I'm not going to repeat it again too much. The p-value is the lowest level of significance at which you begin to reject H0. It's a turning point for H0. So when the level of significance was 5%, this p-value meant H0, you're done, you're out, you're in the rejection region. But if the level of significance was 1%, H0 would have been fine. He would not have been rejected here, okay? So that's how important the p-value is. And if alpha was exactly what the p-value was here, if alpha was 2.4%, then H0 would just begin to be rejected. That's the turning point for H0. So hopefully people can get that into a flashcard and into words and look at the previous two parts of these videos where I do my discussions on p-values. Okay, good. The magazine found that the average speed of this sample, so this is the next question. The magazine found that the average speed of this sample was lower than the previously established speed. So we remember that from previously before. Find the average speed of these cars. Right. So I think, what was our sigma before we might need it? The sigma was 12, just in case we need it for this question. So sigma was 12. Okay. So they got some p-value here. So what we're going to have to do is we're going to try and work out a z-score associated with this p-value, all right? So let's remember what our p-value formula is. So p-value equals, remember it's an area, so the reason it's 2 because we add up the lower and the above area. 1 minus the probability that z is less than the modulus of whatever the test score that we got. So we're actually looking for that now. So we're working back to this guy. We're working back to this guy. So the p-value in this question was 0.024. Okay, and then that's equal to 2 times 1 minus the probability that's z. So this is an interesting type question. It's like we have the p-value and now we have to work back to the z-score. Okay, so then this is 2 times this. So then you'll divide by 2. I'll try and show as many steps as I want because this could be a little bit complicated for people. I don't want to overwhelm people. Okay. So then we're going to bring this over and bring this over to keep it positive. So the probability that z is less than the z-score that we're looking for as a modulus is equal to 1 minus this number, which will be 0.9. I better do that in a calculator so I get it 100% right, 0.012. So we're looking for some z-score that has this area below it. Okay, so we should go to the tables book and see what has 988 below it. Who has 988 below them? That looks pretty close there to me. 988 would probably be this one. So this is 2.26, okay? That's got the 988 below, 2.26. So that, let me get it back here. Yep. This z-score, let me move our sigma out of the way for a minute. This z-score must have been 2.26. 2.26 if it had that area below it. So that's how you take a p-value and work back to the z-score you were working with. Now you got to think about this sometimes. Sometimes it could be the negative or the positive one because remember this was realistically equal to the modulus of what we're looking for. Okay, so realistically the z1 could be above or below. So they kind of give us the hint here that we're to take the lower value, that this sample had the lower one. So realistically we want the negative version of this. Okay, so hopefully that makes sense to people. So that's our z-score. That's really the big battle of this question, was getting that z-score. Okay, so then we use our z-score formula. Now they are talking about a sample here, so because this is a sample mean where this got from, so we're looking for the average speed of this sample. So we're looking for an x bar, people. Okay, so we have to use this formula, x bar minus mu over sigma over root n, okay? So we've just got our z bar, our z. So we sub that into that formula there. Let me get another color. So we're going minus 2.26 equals the x bar that we're looking for, minus the mu, which is in the question, 87.3, all over, as I said, we'd need that sigma from before, which is 12 over the root 100. Over the root 100, the hundredths from up there, okay? So then you can just kind of move this around. I'll move it around pretty bluntly here. X bar equals 12 over root 100, which gets multiplied by the minus 2.26. Then the 87.3 comes over, and then it's 87.3. So then the X bar, which was the sample mean of the 100 cars that they sampled, multiplied by minus 2.26, and then add to it 87.3. So if I type that in there correctly, the X bar, which is what we have down here, is 84.588. So to one decimal place, 84.6. It has units as well of kilometers per hour. Okay, so this overall was a really, really good question, really tough question this year, because of how it made people think about which z-score formula to use, and also how it gave people a p-value and made them work back to a z-score. All super important stuff. Okay. Yeah, really good question. Okay, so I'll clear this away, get on to our next one. Okay, so we're pretty well prepared. So I didn't have another red mark. We're all the way back to 2016 mock paper now. So we're pretty well prepared on the previous parts and currently the stuff we've covered in this video. So that's why we're able to scroll so far along. So this is a good question here. We've already covered something like this, but we'll just do it again because it's kind of unique. And particularly there's a part 2 to this question that's very interesting. So we're going to do this here. So obviously pause the video, give this a go. So they've given us a 95% confidence interval here on the population proportion P. And they say that in a poll carried out by Arrival Marketing, that's all just kind of jargon, a sample of X voters was surveyed. 60% of the sample claimed that they voted in the last general election. Okay, a 95% confidence interval. Okay, so it's interesting what they're saying there. A sample of X voters. So they've basically, from what I'm reading there, they've given us the p hat. It seems to be 0.6. So then what we're really looking at, they must have used this formula, 1.96 square root p hat, 1 minus p hat over n. And we can work out what's called the radius. Remember, we've mentioned this before, the radius of the confidence interval, which is what did they add to this? This is what's known as the radius. Okay, what did we add and subtract to p hat? What did we add and subtract to 0.6 to get these numbers? So we can work that out pretty easy. We just take one of the big values there and take it away from 0.6, and that gives us this radius thing here. That should be a minus sign. Let's type that in. So we get this number of 0.04294, and that is our radius up here. That is this 0.4294. And you can do this as well, like go 0.6 minus this number, you should get the same thing. I'll just do that there, minus 0.55706. And yeah, you basically get the exact same number, okay? So we have the radius of the confidence interval, the p hat is still 0.6. So then, as I said, we've already done a question pretty much like this. So you just set the radius here, 4294 equals to the radius, 1.96, square root 0.6, that's our p hat, 1 minus 0.6, and this is what this question is all about, find n, okay? So the algebra on this, I might show a few steps here. So what I'll do is I'll go 4294 over 1.96 and then square everything. And then that will be equal to 0.6 times 1 minus 0.6 over n. And you could do a pretty blunt force move here to get n on its own. So what you would do is you bring the n up here and then you divide by all of this. So n would be equal to 0.6 bracket 1 minus 0.6 and then all over this thing in a square root. So again, you know, that's where you kind of want to get. You want to be good at moving numbers around like that. It's good for you and it's good for the examiner if you made a, you know, if you incorrectly took down a value as 0.65 or if you incorrectly wrote this with a missing zero or something. It's easy for the examiner to see that you mistyped something into a calculator by showing them that you only need to use the calculator once here, you know. Um, so if you did type something incorrectly into a calculator, you'd lose very little marks because this is numerically the correct answer here, you know. Sound. So it's not a big blunder if you're in the blunder language. 1.96. So that works out pretty bang on as 500. So I'm getting like 500.03. So like it's trying to tell us it's 500 anyway. We wouldn't be considering rounding that anywhere up to 501, you know. Particularly the way they give us this here. So it's pretty close to 500. Okay, so that was relatively easy. We've already done a question like that. So the reason I'm doing this question is because this down here is quite tough, okay? And it's making sense of what they're asking of us down here is why it's quite tough. Okay, so everyone should pause the video and give part 2 a go. Right, how many voters would have to be sampled? Okay, as we worked out here before, it was 500 voters that were sampled, right? X voters. How many voters would have to be sampled in order to cut the margin of error by 25%? So if you're cutting a value by 25%, everyone should know this, right? Say there was a jumper in a shop for €50 and it was 25% off. The way you get 25% of this is you go 50 multiplied by 0.75. You don't go getting 25% of it and taking it away. The quick way to do that, when 25% is off something, there's just 75% of it left, so you just multiply by 0.75. So what we're really doing in this question is we're setting our original margin of error equal to what it originally was multiplied by 0.75. So hopefully people understand that. So what was our original margin of error? The margin of error is the thing that you go plus and minusing. Okay, that is the margin of error. The thing you go plus and minus, we call it ME. The margin of error is this 1.96 p hat. I'll type it in here, 0.6, 1 minus 0.6. So we're really looking for an unknown n, if that makes sense to people. Again, p hat 1 minus, yeah. Now, the margin of error, as we said, the easiest way to do this is just to interpret that this is, if it's 25% less of what it originally was, well, then we just multiply it by 0.75. Okay, like such. Hopefully that makes sense to people. That's going to be what our new margin of error is. So we're kind of looking for what the value of n is that gives this. So we need to actually know what that margin of error becomes. So if you remember before in the last question, let me show you exactly how to type this in here because we want to keep the n unknown. So the original margin of error, if I can remember we got it from taking 0.6 away from this, so you can actually pretty much see it from the thing. So the original margin of error was 0.4294. So if we worked it out and done this exactly like it is now, we get the 500 we got before. But that's not what we're supposed to do. We're supposed to have a 0.75 multiplying this. So let me try and make room for that. So it's this side of the equation that the 0.75 is supposed to go on. Okay. So that's your original margin error. It's been cut down by 25%, so there's just 75% of it left. So you just redo the calculation that we done before, okay, exact same, and you'll get your new n value. So I'm going to do that here. Hopefully I remember how everyone slotted in. It's actually here in my calculator how everyone moved around. So it was something like 0.6. Yeah. So what I mean is, like, you can do this. This isn't super complicated. All you're doing is you have one equation here with how many unknowns? One n. So you just got to do the algebra to get the n on its own. And I already showed you how to do that. What you do is you bring the 1.96 under this, square both sides, and then fire all of that under here and bring the n up. Hopefully people remember that. You can rewind back anyways if you don't understand where I'm getting what I'm getting here from. So originally this was like 0.04 something, but now it's got the 0.75 with it. So it's 0.04294. It's got its 0.75 with it. And then it was divided by the 1.96 and it was squared. Okay. So n equals, this is the most common way people to do this. I'll show you a quicker way of having to do it if you're pretty smart with your ratios. 0.04294 multiplied by 0.75 over 1.96. So then n there works out, again, it's kind of really close to the value it wants to be. It's 88.95, so you're going to pretty much just call that 889, okay? You wouldn't round it down because it's so close. But like it isn't, the question isn't set up for getting us to kind of say, oh, at most it's 25% or something like that, where you actually have to do the thing where you test, do we round up or down, you know? Because rounding up might actually not give the correct value for the question, but that's not what this question is. Okay, so if people managed to get part two out when you paused the video, well done. And this was probably the way you went about doing it if you were pretty good at it. It is still a tough question to realize to take your original margin of error and multiply it by 0.75, which is what reduces it by 25%. Okay, so there was a ratios way of doing this, okay, for anyone who's good at their ratios. The margin of error, right, is always equal to this. So this is a little bonus thing here for anyone who can understand it. This is always true. That is just what the margin of error formula is, okay? And it's the margin of error we go plus and minus on our p hat when we're doing the confidence interval. Right, that's the margin of error. As in this question here, p hat is fixed, right? So the margin of error, again, if you've never seen these proportionalities before, don't panic. This is just you've seen how to do this question previously a second ago. That's the way you'll do it if this doesn't make sense. But this is just another way for people to kind of respect. The margin of error is proportional to 1 over root n, right? So if the question was, we wanted to half the margin of error, right? If you wanted to half the margin of error, you don't just double n, okay? You'd need to put n up by 4. That would half the margin of error because then it's changed by 1 over root 4. So that would half the margin of error, if that makes sense to people, okay? So I think we covered a question on that before where the question was, okay, we need to half something, right? So we want to reduce something here by 25%. So what we really want to do here is we want to put the margin of error. So let me work out how to put this in here so that we can work out something halving. So if this here, remember it's the margin of error that has gone down by 0.75. So just so you understand that as well, 0.75, it's easier to look at it. It's really 3/4 of something. So we've 1 over square rooted something here. Let's call it x, and it worked out as 3 over 4. Okay, so let me put the x in here. We're looking for like a factor here. Remember I showed you that the factor x has to be 4 if you wanted to half the thing. Okay, so we're really looking for the x here. So let's square both sides here. So 1 over xn. Again, this is complicated, but if you don't understand this, no problem. You already seen another way to do this question. So xn, when you tidy this up, should be 16 over 9, or 16 over 9, yeah. So what that means is if you want to reduce the margin of error by 25%, in other words, it's 3/4 of its original value, your sample size needs to go up by 16 over 9 times bigger, okay? And so let's check if that works. Remember we had 500, and then if we multiply, that was our original sample size. If we multiply that by 16 over 9, we get the same value as we got there a second ago. We get 88 point, like, you know, 88.89. So then that's the 889 that we had from a second ago. So it's the same answer without having to do the work. But as I said, that actually looks pretty complicated as it is there because it was 3/4. It's much easier when you're like wanting to half this and it's fairly obvious you put a 4 there. So there's a bit of algebra here. My notation probably as well could be a little bit improved here for explaining this. Yeah, where we wouldn't have actually the n in on this, we would just call it like the x, okay? So then you'd have like that the x there is supposed to equal the 16 over 9. So then your sample size needed to get 16 over 9 bigger. Okay, cool. As I said, that's complicated. It's a thing to appreciate if you're pretty good with the ratios and the proportionalities. You'll see a bit of that if you've done physics. So the physics students will hopefully appreciate something like that. But I showed you how to do it anyways by hand, where you just kind of do 75% of the original margin of error. Okay, I'm waffling a bit, so I'm going to pause this and move on to the next question, okay? So let me pause the video. Yes, so our next question here comes from the official 2016 paper. And it's just a short part down here that I want to discuss because I put an interesting mark here to show people these graphs if they weren't familiar with them in the book. So what they're on about here, this is kind of a bit of its own standalone question, right? It is known that data on farm size, how big the farm is not normally distributed, right? So that means it doesn't follow a bell curve. A research institute could take many large random samples and create a sampling distribution of the means of these sample means. Give one reason why they're able to do that. So this is what's called the central limit theorem. Okay, so let me go and get that from the book. So notice what they said here. You'll need to understand this is what we call the parent population, right? This is the parent population. We also sometimes call it the underlying population. It's the thing we're sampling from, okay? It's the underlying population or the parent population. And what happens is if that thing is not normally distributed like it is in this question, the size of our sample has to be greater than or equal to 30, okay? And that's according to the central limit theorem. Okay, so that's why they say large random samples. What they mean by that is this n greater than 30. So for you to get your full marks in this question, you would need to quote that what they're talking about here is the central limit theorem, and then say that according to the central limit theorem, as long as your sample sizes are greater than 30, greater than or equal to 30, the distribution of your sample means will be normally distributed, even if the underlying parent population was not normally distributed. So I recommend pausing the video, rewinding back what I said there, and make a flashcard on it. And I'm going to go to the book and show you what I mean by what the parent population's distribution would look like here and what the distribution of sample means looks like. So give me a sec. So now we're at the book. So this is what I was on about. This is the central limit theorem. And there is your thing here, what we're on about. If the sample size is bigger than 30, the distribution of sample means, right, will be normally distributed, regardless of what the underlying parent population distribution was, okay? So this is what we mean here. If the underlying population is normal, which wasn't the case in this question, you're okay to have a sample size less than 30, okay? And this diagram is really important here. So this here is what we call the underlying distribution for a question like what we're talking about with the farms. It is not normally distributed, okay? But your distribution of sample means will be normally distributed. This curve here that I'm going to sketch over in purple, that is normally distributed. And the reason that's normally distributed is because in this example here, n was greater than or equal to 30, okay? So that's what you have to have. And just a little bonus thing as well too, people are supposed to know how when you have a skewed distribution like that, where the mode, the mean, the median lie. The very tallest part here will be the mode, then the middle part will be the median, and then the furthest part out here will be the mean when you're skewed off to the right side there. So that's why, look at where they're putting the center of this guy here. They're not putting it here at the tallest part, which is where the mode goes. They're putting it out here where the mean goes, and in the middle of that there would be the median, as you see there. So hopefully that I'm revising a lot of things for people there. You've got to make your flashcards on that, and hopefully you learned something from that there. So that the reason why I highlighted that as an important question you should know is you're obviously meant to know the central limit theorem, and as students you're meant to know the difference between what the underlying parent distribution looks like and what your distribution of sample means looks like, okay? And this here is a clear example of if the parent distribution is not normally distributed, which it's not, n needs to be greater than or equal to 30 for you to get a nice normal curve like this here for your distribution of sample means. Okay, hopefully people are good with that. There's some good learning in that for the students who can understand it. Okay, so that's why this is here. Give one reason why they might do this. So they need the large ones, n greater than or equal to 30, because this is not, the parent population is not normally distributed. So for their distribution of sample means to be normally distributed, they have to take the large samples. Okay, great. Now we've got a little simple question down here in D. Pause the video, give it a go. So a research institute also carried out a survey on how the agricultural land was used, and farmers were surveyed, and it said this was the margin of error. Now we're not told anything about a p-hat here, so we must be talking about the simple margin of error formula, which is the 1 over the root n. which we don't use all that much. So basically they're looking for n here, and they've given us the margin of error. So you just write it in decimal format. 0.45 equals 1 over root n. Some very simple maths here. Bring this up, bring this down. Root n equals 1 over 0.45, and then just square both sides. And then you'll get your n squared. So n here will equal, I'm going to type it in. I'm getting n to be 493.83, and they don't tell us if it's meant to be at least this or at most this, you know. So what we would do as a best guess here, we just round up, okay? But they're usually more specific when they want you to test it. We round down or round up, okay? Great. So yeah, rounding up will make the margin of error slightly less than this value. So that's probably what they wanted it within that, okay? Rounding down to 493 will make it slightly bigger than that, okay? You can test it anyway. You can put the two values in and confirm what I'm saying. Okay, let me clear that away, and we'll do our next question. So I'll pause and scroll along. So we're nearing the end of the document. There won't be too many more. Okay, so I've actually scrolled on to our next question here. It comes from a 2015 sample paper. But I actually thought about something pretty important there. Remember when we were talking about how to identify the difference between who is the parent population and who is the distribution of sample means. So let me go to the book and pick up a very interesting question to tie in with what our previous question was about when we were talking about the underlying the central limit theorem. Okay, so we're at the book, and these are the kind of questions that come up, and I want people to be prepared for this if it comes up. Now, this is the easy scenario here, right? This is the easy scenario because it's clearly obvious that one of them is not normally distributed. A is not normally distributed, and B is, right? So what's going on here is the one that's not normally distributed must be the parent population or the underlying population. And the one that is normally distributed, which is this one in purple, that must be the distribution of sample means, right? Sample means. And what they said, explain why the central limit theorem was used to get B. So because the parent population was not normally distributed, n in this example would have had to have been greater than 30. And it was, as you can see here, it was 40. Now, the reason I brought that, we had already discussed this, okay, how to tell the difference when they're like this, but there's a really spicy question that come up, which is this one, okay? Here we have that the parent population and the distribution of sample means are both normally distributed. So how do we tell them apart? So the answer to this is the sample means distribution will always have a lower standard deviation. So A here is the distribution of sample means, right? Distribution, I'll just write in, you know what I'm saying. Distribution of sample means. So that's the narrower one. It'll always have a reduced spread. The reason it has a reduced spread is because its real standard deviation is sigma over root n. And so the wider one here, that is the parent population. That's what we're sampling from, okay? Or the underlying distribution. So hopefully that makes sense there. You know, they could ask you to talk about that. Which curve represents the distribution of sample means? It's A. It's the one that had the lower spread, okay? So yeah, hopefully people are good with that. And you can see that as well on this previous diagram, which we had in the yellow box. Notice that the distribution of sample means it's a bit skinnier. See, it's got a less of a standard deviation. It's tightly packed around the mean, okay? Great. So that's good learning for people who are making flashcards and that kind of stuff. Anyways, so back to what we're doing here, which is this 2015 sample paper. And we're just talking about a p-value. Find the p-value of this test in part A and explain what the p-value represents the question. So we've done loads of p-value questions, so I've probably done too many p-value questions, but we'll do another one for the sake of it, okay? So they're on about the mean lifetime of bulbs. In the past, it's been 1,500 hours, okay? So that sounds like a kind of a mu that we're going to be testing against, and it's a units of hours. A sample of 100, okay, sounds good. Recently produced, and it had this x bar, so that is a sample mean, okay, so it's not like an individual value, and that's in hours. And it had a standard deviation of 110. So it didn't tell us what the actual sigma was for the the company. It just told us what the sigma was for the samples. So this is our best estimate of what the overall sigma is. So we'll use this in our calculation. Right. So they got a z-score. We'll work out the z-scores because we need it to get the p-value. So z here, we'll be using this formula. Got to state it for the examiner over root n. So z equals 1475 minus 1500 over 110 over root 100. So then z here equals, let me type it in, 75 minus 1500, 110 over root 100. So I'm getting, yeah, we're in the rejection region with this kind of, it's a good z-score. So for us, it's not like minus 500, you know, something silly. So it's obviously less than minus 1.96. So what we'd be doing there is we'd be rejecting H0. Okay, we'd be rejecting H0. And so what we will be concluding is that the mean lifetime of the bulbs is no longer 1500. It's changed. The mean lifetime has changed. Okay. Yeah, so you see they were telling us this there. Test if the mean lifetime has changed. So H0 would be rejected. H0 would like to think that there's been no change. And obviously H0 is getting rejected here, so there must have been a change, which means H1 worked, who talks about wanting a change. Okay, so we're going to do the p-value now. So I already stated the p-value formula for people before. So p-values are equal to 2 times 1 minus the probability. That z is less than our test score here. I'll call it z1. So we're getting a p-value as an area, remember? So everyone should pause the video and do this. And before you actually go and work it out, have a think. Right? This is in the rejection region. The level of significance is 5%. Should this p-value be less than 0.05 or should it be greater than 0.05 if we're rejecting H0? Think about it. Okay, hopefully you realize that if you're in the rejection region, your p-value must be smaller than the level of significance to get out into that rejection region, you know, get out here. This is our rejection region. So we want the p-value to be like located further out here. We want the p-value's area to be like in here, you know, if we're in the rejection region. And indeed it is. So when we work this out here, we go 2 times 1 minus the probability that z is less than. Now we'd use the modulus thing here. My writing's gone a bit messy here, but you get the point. 2.27. Close it off. Go to your tables book. What's below 2.27? It is 9884. Okay, so I'll move up here. It's a bit better. So we'll call it the p-value is equal to 2 times 1 minus 0.9884. Type that into your calculator. 2 bracket 1 minus 0.9884. And yeah, you get a value less than 0.05. You get a 0.232. Okay, and that because that's less than the level of significance, that would mean we have to reject H0. Okay, it's because you're in the rejection region there. But again, bringing us back to where if alpha was 1% here, we would not be rejecting H0. If we were doing a 99% confidence interval, we were doing a 1% level of significance, we would not. And that tells us that the p-value is the lowest level of significance at which we begin to reject H0. It's a turning point. So at 5%, H0 loses, it gets rejected. When the level of significance will be, say, 1%, it wouldn't get rejected, okay? So we've done loads of talking about the p-value, so I'm not going to labor that anymore. So in the context of this question here, because sometimes you're asked this, so remember the p-value there. And a nice way to do this is 0.232 is just state it back. This is the lowest level of significance at which the null hypothesis H0 would begin to be rejected. Okay, so because H0 was already rejected in this question at the 5% level of significance, what you would say is the level of significance would need to be this or lower for us not to have rejected H0. In other words, for the mean of the light bulbs to still be 1500 hours, the level of significance we should have tested at should have been this or lower, okay? Because when it's 5%, H0 loses and it's not 1500 hours. So hopefully you're making sense of that. But a default thing you can always go to here and still pick up marks is just discuss what a p-value is. It's the lowest level of significance at which the null hypothesis gets to be rejected, okay? And then try and build it into the context of the question with the null hypothesis being 50, now 100 hours. And so this is the level of significance that's needed, um, at which we start concluding that 1500 hours is no longer the mean life. Again, it's a little bit wordy, it's a little bit tricky. Pause the videos, rewind it back, try and make sense of it, and try and make a flashcard out of it, okay? Right, what do we got here? Surely we're nearing the end of this, so this is at an hour. I better just push through this because I don't think there's, rather than making another part of this series, okay? So let me just see how many questions are left here. Let me pause. Yeah, what I'm going to do now, because there is like a small handful of questions left, what I am going to do is I'm going to stop the video here. This will end the part 3, and then we'll pick up from here in the part 4 and finish off the last few questions. So this is a really important one because I put 3 stars beside this, so I want to not have people too sleepy, in the parts. So I'll end the video here at about an hour, and then in the next part 4 here, we're going to pick up with this really important question, because you see it has 3 stars beside it, and then there's a handful of questions to finish this out. So part 4 shouldn't be that long. Anyways, I hope you learned a few interesting things in this part, and if you did, be sure to like, subscribe, and comment saying it was helpful. Okay, thanks for watching. Great, so we're back here for basically the part 4, the final part of our inferential statistics past paper questions you should know. So I said we'd pick up from here. This is a very interesting question, particularly the part B. So I recommend everyone pausing the video and giving this a go. But the hint will be that in part B you might need something from your probability, which is Bernoulli trial. Okay, so let's get set up for this. So starts off as a pretty standard statistics question where we're told some car rental company, loads of jargon, manages tires, a way that 4 tires all wear out at the same time. Okay, whatever. The company keeps a record of the lifespan. Now we're getting into what the variable will be. The records show that the lifespan of the sets of tires is normally distributed, right, with the mean of this. Okay, that's got units as well, so our gotta watch out for that. And then sigma is 8,000. Okay, so there's no mention of sample means here, so we're going to be using our regular x minus mu over sigma formula. Okay, right. So yeah, what it's asking here, a car from the economy fleet is chosen at random. Find the probability that the tires on this car will last at least 40,000. So what they're on about there is the probability that a random x value is greater than 40,000. So now we need to standardize this. We need a z-score equivalent for 40,000. So we do that with our z-score formula. They call them standard scores as well. That's what it's called, standardizing. So our x is 40,000 minus the mu over sigma, which is 8,000. So this should be quite likely, because when you think about it, if on average they can do 45,000 and you're just asking does it do at least 40, it should be quite likely. So we'll work out exactly how likely it is. 40,000 minus 45,000 over 8,000. So we get a negative z-score of minus 0.6. Now it says 2.5, but we can only really work to 2 decimal places with the way the tables book is set up. And again, too, don't be putting yourself out of your way trying to get in between values. Just round it. So that goes to 6.3. It's because it was working out 625 in the calculator. So you convert this statement up here into the probability that z is greater than minus 0.63. Now, when you're looking for an area like this, you need to always draw the bell curve, both for you and the examiner, and shade in the area that you're trying to get, just in case you don't get it right. And it also helps you get the area. So it doesn't have to be super to scale, minus 0.63. Now you want the area greater than that, so you're looking for this green area here. Now the problem is the formula tables do not tell us what's above a negative z-score. But because everything is symmetrical, what's above minus 0.63 is the same as what's below plus 0.63. Okay, 0.63. So because everything is symmetrical, the area below that z-score, those green areas are the same. So your next line of workings here for the examiner would be, oh, but that there you just drop down is the exact same as z less than 0.63. And you can just read that from the tables book, and then that's the question done. So what's being less than 0.63? Looks messy, but you all have your own formula tables, so you can just go look at it yourselves. Uh, 6.3, so it's 7.357. And if you wanted a really accurate answer, you wanted the 6.25, you would just do the midpoint there. Anyways, I'm using this here, so 7.357. 7.357. Okay, so the answer is 0.7357. So as I said, it's quite likely. There's a 73.57% chance, right? Let me clear this away. Obviously, you have that all taken down. Oh, actually have a thing here, don't I? So there's a 73.57% chance that a car's tires will last at least 40,000 kilometers. Okay, so it's quite likely, it's over a 3/4 chance. Right. So we need that number. I can't be throwing that number away. 73.57. Let me write it down. So this is a 73.57% chance. Okay. 20 cars from the economy fleet are chosen at random. Find the probability that the tires on at least 18 of these cars will last more than 40,000. So you see this ties in with the chance that we worked out in the previous question. So this is really tough. And I'm sure a lot of people would have been confused. And they're like, oh, are they giving us a sample size here with the 20? No, that's not what this is. This is a Bernoulli trial. And what they want is us to work out, it's really tough this. So the probability that at least 18 cars can do this, we need to do a Bernoulli trial here where it's the probability of, and I've done probability videos on the channel, so if you're confused with your probability, have a look at this. The probability of doing at least 18 cars successes is working out a probability of exactly, EX stands for exactly 18 successes, or plus exactly 19, and then or exactly 20, right? So what we do then is we write down a Bernoulli trial for this thing. So that is out of 20, we want 18 successes. The chance of success is this number up here, 0.7357 to the power of 18, and then we have a failure. Failure is like 1 minus that number. I'll just do it out here in the calculator, so I only have to write it once. Minus 0.7357. We want there to be 2 failures here. So this is exactly 18 successes. Exactly 18 of the cars managed to do at least 40,000 kilometers. Okay, plus this one here, which is 20. So this was a tough question now. I wonder how many people paused and actually got this out. So it's a really smart question. This would be nice to see something like this come up again because it made the students, first of all, do like a Z-score thing, but then tie it in with what their probability stuff is. 20, choose 20 times 0.7357, power 20, and then it's this thing to power 0. You know what it is there. I've ran out of space. I'll write it in though for sake of it. 6, 4, 3. Okay. Great. So you add all that up and you'll get your answer. So I'm obviously going to pause the video and get you an answer for that. I'm typing it in myself into the calculator. Okay, so let me pause. Okay, so we're back. I've worked that out. I'm just looking at this here. I wrote a 2 here. That's a 20. And then that's power 0. So when you type all that in green there, you'll get 0.07057. Did it tell us to round it? It didn't. So there's only like whatever here, like a 7.06% chance of at least 18 of these cars will last over 40,000 kilometers. So it's not that likely, but yeah, that's the answer to it there. Okay, tough question. Tough question. Okay. So hopefully people learn something from that one. It was a bit interesting. Right, so I'm going to obviously pause this now and scroll along to our next question. Okay, so this is just a bit of an easy one here. This is from a 2015 mock. I don't want us to do the hypothesis test, but I just want to make sure everyone's able to state the null and alternative hypothesis with a statement like that above. So everyone pause the video and have a go at writing them out. Right, H0 is the no change, no difference, the conservative statement. He likes there to be no change, no difference. So when we see something up here, a manufacturing company claims that 90% of their customers find their light bulbs good value. H0 is like, yeah, I love that. 90% is the true value, okay? And that's a proportion, so it would say p hat at this, okay? It says there's no change. Basically, the original claim is still true. That's what H0 says. The null hypothesis will say no. It'll say p hat is not 90%. Okay, this will say that 90% of customers do not find their light bulbs good value for money. Does that make sense to people? Obviously, these are the shorthand ways of writing it, but you're meant to write out the longhand version as well. The longhand version of this is 90% of customers find their light bulbs good value. You'd write that there. And then here you'd write 90% of their customers do not find their light bulbs good value. You'd write that there. Okay. And then obviously you can go do, we've already shown you how to do the hypothesis test where you do up the interval using this p hat here. P hat being, I'm not going to do this now, I'm just going to let you do it for homework. 1.96, but we've already done questions like this, particularly in the part 1, where we do hypothesis tests with proportions like this. And you'll create yourself an interval there with 2 values either side, and then you'll check if the 90% is within the interval. If it's within the interval, H0 wins. If 90% is not contained within the interval, you reject H0 and you do not reject the alternative hypothesis. Okay. Happy days. So I'll scroll along to our next question. So let me pause here. Yeah, so we're nearing the end of the document now. So in 2013, there was this interesting question. You can zoom in on it there. They're doing something with a plant and some hormone to change how it behaves. But basically, we can just follow the instructions from the graphs here. Okay, so we've already done one like this where we manipulate the shape of the graph based on what something does. So they say that, obviously pause the video, do each of these before I start drawing. Right, hormone A. The effect of hormone A was to increase the height of all plants, right? So mu is the height of the plants, okay? Mu is the height of the plants. So if you have gone and increased the height of all plants, what that does, that shifts the mean. Okay, you have a bigger mean now. So I wanted that to be perfectly symmetrical there, where it follows the graph. See, it deviated, but it shouldn't. That's just me and my sketch. So then it's going to have, say, a bigger mean here of, this is the new mu, and you bring it over. So that's what the examiner will be expecting you to sketch. Not taught the same height, the exact same shape, just shifted to the right. Okay, that will get you full marks. Right. Hormone B. The effect of hormone B was to reduce the number of really small plants and the number of really tall plants. In other words, they want to and keep the mean unchanged. So give a go with this. So what they want to do is reduce the spread here. They want to not have the thing so wide, but they want to keep the same mu. So what this does is it makes a taller, narrower distribution like this. And that will get you full marks. Okay. Hormone C. Pause the video, give this a go. The effect of hormone C was to increase the number of small plants and the number of tall plants. So in other words, make there to be a taller bars down here on your histogram. So the mean was unchanged. So this basically just wants to make things wider, like such, and it won't be as tall. That makes sense. So I want to make this symmetrical out here. That'll do. So it's still a bell curve, but you see it can't be as tall now because it's gotten wider. So in other words, you can see, because this is really a histogram with the bars, there's now, and the height of the bars are how frequent they occur. So now with it getting wider like this, there are more smaller plants. We've increased the number of them, and we've increased the number of taller plants by making it wider. And it obviously has to get, the distribution has to get smaller in height, as I drew there a second ago. Okay. So that's a good question. That's a really good question if it comes up. So good, you're well prepared for that if it comes up now. Okay, so let me pause, find our next question. Okay, so this seems to be a 2013 official paper 2 project maths thing. So it's kind of a standalone question I want to do from this. It's just this part 2. So pause the video, give this a go. So a manager of the airline says, if we survey 2,000 passengers from June on, we will have the margin of error. So you need some little information from this up here. So hopefully you rewinded the video to when I glanced at this up here. What he's originally done was sampled 100 people, right? And he's talking about the margin of error. Okay. So if we scroll down here slowly, you'll kind of see what we're on about. If we survey 2,000 passengers for June, we will have the margin of error. So we should all know our margin of error formula. So let me get it up here. So that's 1 over root n, as we've been saying before. So this is our margin of error formula. If we're dealing with more accurate, like the proportions, now in this question they said nothing about p hats, so we use the less accurate version of this. We don't use the 1.96 square root p hat 1 minus p hat over n. We use this version. So basically he's like, okay, we had originally n was 100. Well, 1,000, and now he's increased n to 2,000. So we've already done questions like this where doubling n does not half, or like it doesn't half the margin of error. Okay, this is like this proportionality thing. So basically, he's doubled his n. So originally, what we're really dealing with here is he's gone 1 over root 2n is the new margin of error. So all he's really done to his margin of error is divide it by root 2. Okay, that's the new margin of error. Hopefully this makes sense to people. So he has not halved it. We've already spoken about how you half the margin of error, I think even in part 1. If he wants to halve his margin of error, he doesn't want a 2 to be here. What number does he need to be here if you want to not get a root 2 here but get a full-blown 2? You need to put a 4 there. Because if you increase your sample size by 4 times, then you get a root 4n here. And so then the root 4 is a full 2. So that is what you need, is a full 2. So he would have needed the correct number. The answer is no here, is he's not correct. And he should have sampled 4,000 passengers if he wanted to half his margin of error, okay? Because that's just how it works. The original margin of error was 1 over root n. And so if you want a margin of error that is this new halved amount, 1 over 2 root n, you had to increase this by 4. There had to be a 4 here, if that makes sense. Because then the rule of indices there is you got root 4 root n, and so then a root 4 is the 2 that appeared here. So there had to be a 4 there. Okay, so I've already kind of discussed that. It's a little bit tricky that to kind of explain it there if you're not too comfortable with the ratios and that, you know. But we've already covered that if you watch some of the previous parts on this and the previous questions where we're dealing with they're doing something to the number of people sampled. How does it change the margin of error? There's been a few questions like that, so you can go and look at them and practice them as well as this one. But yeah, to half the margin of error, you need to increase the amount surveyed by 4 times, not just double it here, okay? Great, so I'll pause this, find our next question. So thankfully this is our last question now, so we'll be wrapping up on this. It's at the end of the document. It's the last one. I've put a star beside it. This is all the way back to 2010. So it's quite a unique one, this. I read this and I liked it because of what they give us in the question. So they're kind of making, obviously pause the video everyone and give this a go and have a read of it. But what they've done here that's quite unique, we're only answering the C here, this is just context up here, is they've given us as if someone went into the machine shop and actually recorded some values. And from this, we're going to work out our own X bar. We're going to actually work out X bar by hand. So we had a sample size here of n equals 8, okay? Now, because n is so small, the parent distribution, as we spoke about previously in the previous parts, has to be normally distributed. And if you read this carefully, it's a factory with aluminium rods. The machine produces the rods. The lengths of the rods are normally distributed. So that's why it could be a little bonus question. Why can we get away with just sampling 8? Well, according to the central limit theorem, it usually has to be greater than or equal to 30 if the parent distribution isn't normally distributed. But if it is normally distributed, the parent distribution, we don't have to sample 30 or more. So n equals 8 was fine here. Right. The lengths of the bars, we're talking about the lengths here, with mean equal to a specific length and a standard deviation of 0.2. The machine has been set to produce this. So this here is like the original mu that the machine is supposed to produce. It's got units of millimeters, so good to record that. The sigma, it's a very tight sigma this as well. That's not a big sigma, okay? So if it's only 0.2 mil, X bar is not allowed to vary a lot here, you'll see. The operators want to check whether the machine is still correct. They go into the shop and then they sample 10 rods here. Oh, sorry, was I right in 8? That's 10. But still, it's the same thing as what I was on about there. You know, it's not bigger than 30, but it didn't have to be because of the normal distribution. But there's obviously 10 values there. Silly me. Okay. They take the 10 rods and they record these. They went and measured 10 rods. So conduct a hypothesis test for this. Okay. So what would H0 be? H0 would say there's been no change, no difference. So he's going to say mu is still 40 millimeters. And you would have to state that as a statement. The mean length of the rods is 40 millimeter from this machine. And this one is going to be like, no, it's changed. It does not equal 40 millimeters. Okay. And whether the machine setting has become inaccurate. Yeah, and so that will be the thing. The machine, H0 would say the machine setting is not inaccurate. it is still producing 40 millimeter rods. And H1 would say mu does not equal 40 millimeter. And this would say the machine has become inaccurate and is no longer producing 40 millimeter bars. Okay, so let's work out a Z score as we usually do. Z equals X bar minus mu, because we're dealing with sample means here. We just worked out our sample means, so it's obviously this formula with the root n. So then Z here equals, I've got to work this out. This is a bit annoying. So you got to add all of them together and then divide by 10. So let me do that. I'm sure everyone can work out the mean of 10 numbers at Leave Insert higher level. Okay, so I got the mean of those numbers there, and I got 39.87. Okay, it works out. You don't have to round it. It works out neat like that. So then Z here equals X bar, which is 39.87, minus the test value, the mu of 40, over the sigma, which was given in the question, 0.2, and then it's over the square root of our sample size, which was not 8, nearly done it again, over 10. Okay, so then Z here equals 39.87 minus 40, 0.2 over root 10. Oh, so this isn't good now because we were getting a, well, look, it just means we're rejecting the thing, you know. It doesn't mean it's not good or bad. If that was like minus 50, we'd know something was not good for us solving the problem, you know. But this is not good for the machine because the machine has become inaccurate, okay? So this here is less than minus 1.96. So so therefore we reject H0, and you got to say we reject H0 at, that's the at symbol, at the 5% level of significance. This is our conclusion, at the 5% level of significance. So you can, I'm just going to call out in words to you, at the 5% level of significance, we reject H0 and we do not reject H1. Therefore, and you read out what H1 means, the machine has become inaccurate and it is no longer producing 40 millimeter length bars on average. And that'll get you your full marks. Okay, so that was a cool question. I done that because they actually made us work out the X bar, which is quite unique. Okay, so that covers us. If you've watched all those 4 parts on this past paper questions you should know on inferential statistics, you should be really well prepared for the types of questions that come up because we've basically covered all the types of questions that come up. So hopefully this helped people out, and if you enjoyed the videos and learned something, be sure to leave a like, subscribe, and leave a nice comment that it helped. Okay, thanks for watching. Best of luck.